I think the session chair is still missing. Is that right? Or
I don't know if he's there. Let's see. Do we have Hunhai here, maybe, to comment about that?
Okay, I try to call him. Okay, try to call.
He's indeed supposed to give a talk, so.
Gianmarco, would you basically start sharing so that we don't delay too much, maybe?
Yes, but I haven't prepared anything, so
Okay.
I mean, I cannot show anything.
But there's no introduction, that's right. Okay.
Yeah, so I mean, we can simply skip the introduction, and so we can, you know, if we reach 9:15, we start with the talk directly. I mean, I can introduce the speakers, and that
Yes.
this is what I can.
I think that obviously that's what I meant actually. Okay.
Yes. So we still have time then.
Yeah, please do.
Okay, so our introduction chairman is not available yet. So in the meantime, we will wait a bit. And in case he doesn't show up, I will introduce the three speakers of this morning session.
Okay, shall I start or not?
No, because otherwise we're going to be ahead of the schedule.
Okay.
We can wait.
Okay.
I mean,
okay. I can't wait. I can't wait.
Manage to reach? Did you manage to reach
Yes. We contacted with him already. Okay. He should be online soon.
Okay.
He should be online soon.
Okay, so let's wait then, and then you will make a shorter introduction then.
So maybe just a short explanation to those who are here already. So we will start in a moment, but the reason why we haven't started is that the chairperson who should introduce the whole session isn't there yet, but he will hopefully be there in a very moment. So we still wait for him, and then of course the three speakers are here.
The session chair is online.
Yeah. Okay, so sorry everybody. So I'm very sorry for I'm late. So let's start the morning session on day 3. Okay, so today we will have 3 talks in the morning. First talk from Professor Tong-Yi Zhang from Shanghai University. And the second talk is about NOMAD, and third one is about AiiDA. So I'm the chair of this session. I'm Yi Liu from Shanghai University. So I'm supposed to have a introduction in the first 15 minutes. So let me share my screen.
Yeah, for the sake of the schedule, I would propose that you don't take 15 minutes. Huh?
Okay. So probably just 5 minutes then. Sorry. Yeah, so probably very, very quick then. So I think so since time is limit, probably I will skip most of them. I think the topic in this conference also most of us have interest in data-driven material science. So so data science is as the fourth research paradigm. Even it came late. Well, in my opinion, the data science centralize the experiment, theory, and the computation. Okay, so the data science can be used to understand both experiment and computation, and then can do prediction, therefore can design the new experiment and computation. Of course, also data science actually can derive derive a theory by deduction or induction process. So it's even it came late. It's a kind of digital representation of human knowledge since the numbers was invented 1,000 years ago, but never accumulated to so big scale and never been so analyzed in a systematic way or statistical way. So I think that so the data science even came late, but it's important to different field. Also, I think I think another thing is as a material scientist. So not only we do the machine learning, we develop a very accurate machine learning model to predict properties accurately, but we also need to understand what's the physics of material science behind the machine learning model. So so that's why I in my language, so we propose we need to go from machine learning to learning from machine. So as a human being, we should be humble. We learn what machine learned, and then find the new physics and new knowledge behind the machine learning model. I think that's also important. So in view of computer science, probably they call the model interpretation. Okay. Also, I think that we have a various data sources came from either public or private. We all learn many big database today, but also we should pay attention to the small data set in the laboratory, in the individual laboratory. Those are also important, should be analyzed and find useful physics. So of course, the NOMAD is a representation of a big data repository or database so far. And the Professor Scheffler and Jaxel proposed this push this idea. So basically push the idea of a big data driven material science. So it based on the collection of bigger computational data, now we are having more experiment data, and so we can do a correlate statistical analysis, and eventually we will draw this kind of a map of materials. So I think that this gives us the new opportunity to do the new material science. But as a last sentence, I would like to mention, so in many times in material science, we don't have a big data. And the small data also important. How to find out the new physics or material science behind the small data? That's also a practical question and important. I think the first talk by Professor Tong-Yi Zhang will talk about this small data with a big noise. So I think that's also an important thing to pay attention. And so I think I used 5 minutes. So let's welcome the first speaker, Professor Tong-Yi Zhang from Shanghai University. So he's a Chinese academician. He's an expert in solid mechanics and material science. And he's leading material genomes and material informatics movement in China. So let's welcome. So I will stop the screen sharing. So please share your screen. Professor Tong-Yi Zhang.
Okay, thank you. I'm very happy to have the chance to share with all of you how to handle with small data and also big noise. So we all know the MDI is proposed by the former American President Obama. So the key issue is how to make the materials research use half time and at a half cost. So from talk about this data and the knowledge, the key issue is how we can gain knowledge from data. So now we are talking about machine learning, but actually, as I mentioned here, learning can be done by individual human beings, especially genius. And at the moment, of course, can all and by machine that we should have joined. The human being, we utilize all the machine, software, computer to learn all the data together. So the learn's purpose is to understanding why things happen. This is for explanation. To predict what will happen. This is for predict. For the first one for explanation. The second one for prediction. And now the third one purpose is to manage things that are happening. This is for control. Now we have a lot of for those. For control the cars, airplanes, ships, and so on. So the development of nature science is a continuous and endless progress that human beings observe nature behavior, develop learning models, and then gain knowledge. I put here Newton's figure here. So we all know the simple is Newton's law, F equal ma, is not derived. It's actually proposed by Newton based on his observation. It's not himself, it's all human being. Okay, we observe the nature behavior, then summarize them, then gain the knowledge. Okay, then gain knowledge. We use knowledge, we express the knowledge by using a simple equations. So data-driven the formula discovery, now we are also trying to develop some algorithm and our program to find the formulas. So we can see historically mostly the important data under the formula mostly are data driven. Of course, now as an expert, we can use expert based formula discovery to gain that directly get some knowledge based on some principles. But here, at least most of them, they are really, we get this from data. Now I put here as one example. I'm working on mechanical behavior of materials. So the major failure mode is a fatigue failure. So fatigue failure, there's a famous law we call Paris law. The Paris law for fatigue crack growth. So you can see that. So here is the vertical line. That is the crack is a growth rate. Now there is a stress intensity factor rigid. Then Paris, based on data, he proposed this simple equation, the power law equation. It basically is a power law. So now at the moment, the academic and also industry are widely use the Paris law, okay, in the theoretical study and also in industry practice. So another is also very, very famous is equation, especially in the metals industry or the materials community metals, okay, metal. That we call that is a Hall-Pitch equation. Now we know most of our widely used metallic materials is for structure. Okay, that's what usually we call that the structure materials, where the human being utilize their mechanical property in our daily life, industry, and so on. So there, the most we use that is the metallic materials are polycrystalline materials. They are not a single crystal, not like in semiconductor, we widely use a single crystal. Now here is a polycrystal. The Hall and the Patch, those two scholars, they are individual developed, they found this equation. All the mechanical property will get better if when the grain size get smaller and smaller. They get this is purely from data. More interestingly, later on, the Hall-Pitch equation can be explained by some theoretical modeling. If they are based on the dislocation modeling, now we have a different model. We use a different model, we can derive the Hall-Pitch equation. The Hall-Pitch equation is further, we have the equation from data. Then later on, we have the theoretical improvement. Okay, we can approve this equation are correct. So the entire metallic industry, what they are doing, they are doing is try to make those metallic materials, how to reduce their grain size. If they can reduce their grain size to lower than micrometer, then they have a super mechanical properties. Those materials will have that super material property. Except the creep, okay? If we want to design some materials against the creep failure, it is better still use the single crystal. But for other materials is mechanical properties. Okay, they are also related to reduce the grain size, make the grain size smaller. The smaller, the better. Of course, now academically, we also have found if the grain size is too small, we have we call that a reversed Hall-Pitch equation. We are not talking about it because to make such so small nanometer scales is those construction materials is not so easy. Okay, now we are still the entire metallic industry is still working on this. Okay, how to make this D small, the grain size small. Now we all know that the AI, artificial intelligence, is a new powerful tool. So I draw, you see, these figures here. Now, no matter you work on, you see, which kind of materials, you have your so many different tools. That is wonderful. But now, where you see, we would like, you see, you to learn another new tool to, you say, how to, you say, optimize, you say, how to use this new tool, put this, you say, AI, machine learning into your toolbox. So the fast developed data science, artificial intelligence, machine learning, and the materials and mechanics, I call that informatics. Now we are widely known. So materials informatics is developed so fast. I see this milestone that is we call this AlphaGo. This is software. Okay, we all know that. You see, one app software can be the champion, the world champion of game Go. Okay, so even you take a look, you see this one, the updated version they call AlphaGo 0. You read this is the title of this article. They call the mastering the game of Go without human knowledge. But before in the old, you see, the original, you see, our system Go in that software, they have used a lot of, you see, the human beings' experience in their database. But for this AlphaGo 0, they only know human being only just teaching the machine what's the rule of the game of Go. Then the two machines, they will pick it to each other. Then finally, after they trained, then they can say the AlphaGo 0 software will win. This is the old version. Also, I like this is a paper. I like the title. They call lessons learned. This is talk about the medical doctor, also skin. You see that a medical doctor, how to diagnose this skin, okay, the human being's skin. So if you read this paper, then you will find that they have a very large database. They all pictures about the human being's skin. Okay, then the medical is a doctor, the skin doctor, when they diagnose that they see your skin, when they treat that, they convert that to a imaging process. Okay, they just make a comparison. Okay, then they will know what kind of, you see, your skin has which kind of problem. Then they will give you, you see, a medical treatment. So I also like this one. This one is they talk about the learning from failure. Learning from failure, they talk about this article, talk about they want to synthesize some materials, okay, some materials. Now, sometimes they are successful, sometimes they say they are failed. They want to find at which condition, what's the boundary between the successful and failed, okay? So if you want to say, find this boundary, so you need the data of the failed data, the failure data. So to data sets or you only data I will talk about is whether your data is reliable or not. Without not means is well, we are not separate successful data or failure data. We are more focused on whether your data are reliable or not. So this is a new article. We talk about, as a title is mentioned, this is a mobile robotics chemist. So that is our goal. As I will mention that now currently we do adaptive design, but actually it's not a cross loop. But in this article, they talk about how to cross loop to do this materials development. So inside here, they have a lot of machine, they are the robotics, okay, big one and the small one, okay. Those then you give them a recipe, then they will fabricate this materials. Then they will testing the materials. If they are not successful, they will recommend what is the next recipe, or they will synthesize. Okay, what's a new materials for the new design? Okay, we are mentioning that. I try to say develop all the similar this lab at the Shanghai University, but we are still working on this. We are still working on this. So now this I just mentioned. Okay, now we are in materials community. I call that is materials informatics. I'm also working on the mechanical behavior of materials. So I also in the mechanics community, I can say call them mechanics informatics. Okay. The materials mechanics informatics actually integrates artificial intelligence to material science and engineering, or maybe to mechanics. Okay. This we show that is adaptive materials mechanics is a discovery. So here is in the center is a domain knowledge. No matter you're working on which kind of materials, so your knowledge is extremely important. It's a harbor. Okay, it's really the harbor, the domain knowledge. But in addition to that, we are suggesting you to do a data driven, to have the database. Of course, you have your goal. Then those data should come from experimental or competition. Okay, that is we are very, very important. Okay, where those data can come from experimental or competition. Once you have this data, you will do a data pre-processing, then do build up a machine learning model. Then you have to evaluate this model. Then based on the model's results, you will make a suggestion. What's the next experimental or competition? What I should do? Okay. Now, based on those recommendation from the machine learning model, then you will carry on. The next round is experimental or computation. Then if you reach your goal, then you will come out. If not reach your goal, then your data will be put into the database again. Then you do this iteration, you do the iteration. So because our goal maybe change. This year, our goal is at this level. Next year, we should put our level is higher. So this one is a dynamic. It's a never end. It's a dynamic, never end goal. So let's talk about this a little bit. Is machine learning. Machine learning usually talk to those computer scientists. They will tell me, okay, those they treat that system as a gold black box. So they have input variables, they have output. Actually, the output variable is actually you privacy, you should know that. Then I usually say as machine learning says that's estimation. I put a hat there, okay? But anyway, so there the key issue is you have 100 is a variable. You have a lot of there is a wrong. I should put it. This should be H. I'm sorry for the mistake. So there you have 100 variable. So those 100 variables make those have an intrinsic area. They have an intrinsic area. Here, there's some people tell me to the stock market, the intrinsic area is very, very large. Okay, that could be reached 200%. But we are do science and engineer. With well-controlled experimental computation, then we can make this, I said, approximately equal to 0. It's not that the case. So we can make it as small as possible. We try our best to reduce this area. Okay, to reduce this area. So there is a big difference. So in my whole life, I'm working on something is really true or not. We believe something, okay. But in machine learning, it's not that case. Machine learning believe the real function, you never get it. You never know it. Only you can get is optimal, is a possible, is a approximate is a function. So there are so many possible approximate functions. So machine learning's job is try to find the optimal one. Is try to find the optimal one. So therefore, they have a bias they have a variance, okay? And this is a simple equation tell you if you make a base area higher, then the variance area will get smaller. So now they have a base variance dilemma. They have a variance. When I talk about the students, I mentioned that, like you say, a student want to make a boy or girlfriend. If he just want to make that is a friend in his or her classmate among his class. Now the advantage is the information is sufficient. He know all the classmates in her or his class very well. But the problem is he may not find his or her girlfriend or boyfriend in just the class, okay, the classmate among the class. Don't have we get the search space get larger, okay? Maybe it's the entire school that get larger. When you get a search space get larger, the problem is your information will get smaller, okay? That's what we call the information entropy will come in, okay? Very, very important, okay? So that's why they have the base variance dilemma. So how we do that, okay? But usually, what they say there are difficulties. The data is smaller. Now I will specifically mention that how to handle. They have two different types of small data. I will give you more detail about this. And also the influence. Okay, there are so many factors we call feature. Okay, maybe some of our friends call descriptors, attributors. To me, I think they are more or less the same. Okay, so I just simply call them features. Okay, that is an influence. Okay, factor. So they are high dimension, very high dimension. And also the noise is big. What means the noise big? To me, I just want to mention the noise big means if you repeat to do the experiment, okay, their experiment scale is bigger. That is a big noise, big noise. So now we are handled with data. We are handled with data. Now they have two critical issues. One is how to select this is a feature. Okay. Another is how associated with this is how we decided to a large space we will do our search. That is another is a feature space. So keep that in mind. Now we are handled with data. The solution usually is not unique. Okay, you can find a different model, the machine learning model that feed those data perfectly. Okay, so you have to keep that in mind. So now we talk about those small data. Here, what I mean is small data. They have two kinds of small data. The first one is I schematically show here. Okay, the number of repeated testing is not enough due to greater scattering in the experiment results. So therefore, the mean of the repeated testing results is not statistically reliable. That is the problem. Okay, we do a summary. Just say where we do experiment, you just do a summary actually. If you are ordinary, that is the greater scattering. If your number, of course, if from statistical point of view, if you are summary number approaching infinity, that's always true. But we cannot do that. We always handle small data. Another data is just they call, actually this is widely called, that case is a sparsity data. That is in machine learning. For this one, we do have some approach we can handle. The approach usually we call is transfer learning and so on. How to enhance those data. We have so many different technologies. Machine learning is algorithm to handle this. Okay, so this one, even though data is smaller, but they are reliable. So that is easier. Okay, that is to me is relatively easier. Okay, the challenge is if their data is not reliable. What can we do? So now I take one loop, one approach. This is by my friends, Professor Luckman. So this that is Professor Scheidgen, is Professor Luckman's is a former student. Now there is a published that paper. So their goal that they propose the adaptive design. The goal in this is an article talk about how to make this delta T small. Okay, how to make this delta T small. So they have originally have 22 initial data. So now there is they take that is 6 features. Then their search space is roughly say 80 100,000 alloys. That is to me that is a very big. The search space is too big, but because the initial data, the number of their data is too small. So then every time they can suggest to do another 4 experiments. Okay, they can go into that, they do an iteration. So now in the lowest is in the 6th iteration. We found that it is the lowest one, delta T. That is in their supporting information. Okay, I copied here. So I said, okay, maybe we can do in a different way. I take all their data. We also put some constraint, we put some limit. We said that we already consider that B2 to R fissure formation. We are not called this other types of multi-statistical fissure formation. Okay, now in this way, we reduce this, we move this 5 data out. Then feature, we just use the element. Okay, we use the 3 alloy element. The target is the same. Further, I do is a decision tree. Okay, the purpose to do a decision tree is try to reduce this search space. It's reduce the search space. That is the original one. So I put the delta T should be smaller than 4 Kelvin. Okay. Now then if that one we get this, we do that. Then finally we will get this. Okay. On this is a leaf. Okay. On this, then we have a totally have a 35 data. Okay. Then in the 35 data, you can see that the gene index is decreased. Then that indicates the information gain. So inside the 35 we see data, they have one data, I call that outlier, that's very, very high. Okay, we have to specially say attention to put on this data. Maybe they have some new mechanisms behind that. Maybe their experiment have not done so well. Okay, so they keep that in mind. So I just remove for the time being. Now we do this similar, we use same machine learning algorithm. So that is the published is in their paper. So that is the predicted number. That is their actually experiment is measured. I use the same machine learning algorithm. We can predict another 5. Okay, actually the predictions is delta T is lower than their predictions delta T. Okay, that's just one of the example. Another challenge is this. Okay, we want to show you the same data can be explained by different machine learning model, not just by machine learning model. Actually, they can explain can be fit by different theoretical model. So that is the model, the formula proposed by Marshall and Law. Okay, both are my very close friends. Okay, we are all working on some mechanical behavioral materials. So that's why I propose another model. From the equation, you can see they are totally different equation. Okay, I use the same experiment. Okay, the same experiment, but the plot is why you based on this is equation, another based on another equation. Then from the data fitting point of view, from the fitting, you cannot tell which one is better, which one is worse. They all fit perfect. Okay, so keep that in mind. Not machine learning can give you different results. Even you do a theoretical study based on your different assumption, they also can get different results, a different formula. So keep that in mind. There are another example. So this is an equation. Now they are from my This Bernice, very famous is a professor at the Stanford University. Another Professor Gao, you're also working in Germany, probably in Max Planck Institute. So they propose that is a famous equation, and based on this equation, they developed the string gradient plasticity. So when I see they are working on this small one, at that time I said, maybe I should do something. So I propose another equation. You can see the equation looks also different from their Professor Nix and Professor Gauss's formula. Okay, that's my equation. So now I ask my formula students, this is Wei Hua Xu, I ask him to collect all the data available at that time. Now here are just a show of them. One is fit by this equation, another fit by this equation, the total equation. Okay, now you can see that. So from the data fitting, you can now tell which equation is better. Okay, they all develop that equation based on different theoretical assumption, a simplification. Keep that in mind. If you do a survey, theoretical study. Okay, so that's just want to tell you if we do a data, okay, driving the formula development, if you get more equation, not a surprise. Okay. So even though you do a purely theoretical study, you could go maybe also get different equations. Okay, keep that in mind. So now I come to this one. So this is actually one of my friends, it's Professor Bazat from Northwestern. He's a very, very famous scientist, and Professor Hu from Australia. So now they argue to each other how to about this is size dependent. Okay, there is actually, but that they have the classical work on side effect, okay, in fracture mechanics. So basically, when the size gets small, we think that is strings dominant. When they say size get bigger, I believe that there is a fracture mechanics will come in, okay, to do the prediction. So that is this very classical work. So the who are the one they also they call that the boundary effect model. Okay, when they say put this is a problem to me, they ask me to judge which one is better. Okay, now I'm doing machine learning. I said, oh, I will not personally, I will not do anything like a machine to do it. So I do a machine learning. We use that is basically talk about 3-point banding. 3-point banding, this is how to experiment setup. That is they have a pre-notch. They have this sample size. They also have this height. Okay, we use all the data is from Professor Bazat's data. That's you can see that is the small sample. This is a bigger samples. Okay, they have really a size effect there. So and also the notch is nominated by that is by this W by the height. So we use the alpha. So you can see that this experiment data. Even though you can see that this repeater, that is the number of repeater testing is not so small. But however, the congregate just so the data scaling so big. Okay, so big. So now if you based on linear fracture mechanics, then you should suppose you should get this. It's not you not satisfy this. Okay, based on this, I said I put that is the common sense. We all know that. Okay, because the data is small and the noise is big. So we put a here, we all agree. Okay, the standard derivation does not follow. Okay, in the common sense, the possible is the bigger defect existing. Okay, and so on based on this. Okay, so I put a 4 hypotheses here. That is the larger the congruent sample size is, the lower the strength will be. The larger the congruent sample size is, the smaller the variation will be. The deeper the pre-notch length is, the lower the strength will be. The degree in data scattering should be decreased with the increase of pre-notch length. This is a hypothesis, okay? Because you take a look at their data, they don't follow this. They don't follow this. So therefore, I use the power law, a normal distribution. Okay, that's the simplest one. We use the power law and the normal distribution. We link them together. Okay, link them together. Then from here, because it's a small data, you don't know there is a distribution. How the advantage when we propose this, the link together normal distribution, okay, with this power law, then we can, that means when we determine, for example, determine this is a probability density, we have used all the data, okay, including the different density sizes data. We will have used that. So that's why we can distribute, okay, their normal distribution, what's going on. Then we can determine this. All those is those that we call that is those parameters we introduced. We determine that based on experimental data, so we can determine their value. Okay, we can determine their value. Then we also can put the size pre-notulance dependent. That is a normal distribution model. We'll do the same thing. Then we can use the statistical testing. Oh, sorry for there are some Chinese word. Okay, but it's just statistical testing to say whether we accept that or not. So then we also do that. So finally we can say found where model is really statistically accept two data. Okay, we put highlight in red. Okay, highlight in red. So now once you have this distribution, then you will know what's really the value at 1%. Here it's 1%. Just you can take it. If you think it's too large, you can put it 0.1%. So failure probability in the congruent strings. Okay, then you can put it there. Their behavior is really like this. Okay, then you can put the probability. Once you know that, then you can always do it. So now the fracture properties, they have two. One we call in fracture community, we call K1C, the fracture toughness. Another, well, those is a crack propagation. In front of the notch, they have a fracture, they have the fracture processing zone. Okay, what's the size of the zone? So we use this finite element to do a calculation, calculate the stress intensity factor. Then we put this is the fracture processing zone. Then because we argue the K1C fracture toughness is a materials property. It's a constant. They're only related to materials. So we put it there. Then we can, that is a way from the finite calculation, we have calculate the stress intensity factor. Then with the experimental data, we can determine what's the fracture toughness and what is the cracking processing zone size. Okay, the delta A we introduced. Okay, so this the results seems pretty good. Okay, this I emphasize that. Okay, the concrete remarks how do machine learning small data with big noise? To me, it's still a great a challenge. Okay, I hope it's more of our friends or colleagues worldwide that can pay more attention to this. And in my personal opinion, integrated domain knowledge with machine learning is the best approach. Okay, thank you.
Okay, thanks, Professor Tong-Yi Zhang. So we still have a few minutes for the questions for this talk.
I don't see any questions here in Louvain. Is there anyone
Okay.
in the online audience?
Well, I don't have a question, but I do have some comment. I think Professor Tong-Yi Zhang's talk actually addressed the issue. So in material science, in many researchers' own lab, so it's very often we have a small data, especially for experiment, right? It's because material data, experiment data are generated it's very expensive, right? So, but now we have this data science concept. So we need to rethink how to deal with this experiment data using the data art, data science, or this big data tools, or even small data tools, because these tools are not familiar for material scientists before, actually. So I think that's also direction or something we need to think in the field. I mean, not because the big data is still, not available to everybody or still ongoing. But we still, I think there are rooms to find the power of statistical analysis for the small data, and that will benefit the material science. Well, that's my personal comment.
So should we put more emphasis on this in the education as well? In let's say how we educate our undergraduates?
Yeah, so I think it's important to tell the student. So for example, we are also teaching material science student. Now we emphasize a lot about this data science. So about machine learning, data mining, etc. So tell them this is really independent, important tools you have to learn and use in the future in your own material science research. So I think the students should learn this as a basic tools, just like computational tools or experiment tools. So data science tool is new independent tools. Still, I'm not sure the other place, but in China, my personal experience, still people kind of mix computational tools and the data science tools. They think they are the same, while they are both use computers for sure, but they don't do real experiment, but actually they are different. So we know. So I think should educate people learn more about the data science. They do have independent tools, concept, and application cases. So yeah, so education is still needed for the material science. And if I add a little bit more comment, I think one example Professor Tong-Yi mentioned is noise. So in experiment data, there are a lot of errors. There's noisy data. So these errors, well, it can be enemy of the data science, but sometimes may be useful. So how to deal with this is a common problem, noisy experiment data. So how to handle this from data science point of view. I think recently, as far as I know, Professor Xue in China, he used this error, put this error into the data analysis and make some progress. Personally, in my personal group, I also try put this error back into the feature as input to the machine learning model, but it turns out it's not successful. But we are learning things. I mean, we need to learn the nature of the data and to see how to deal with this sort of things. Okay, that's my comment. So, so then my point is, so we are, I think, as material data, we are facing challenge from not both big data and small data. Because for the small data, even more challenging because we don't have many data. Then how can we dig out useful information. I think that also rely on the advanced algorithm, also domain knowledge. We need to input the domain knowledge to expand the value of data. So it's not just the number, so the size of the data, also the quality, and also how to take good advantage of limited data. I think that's also sort of things we need to address, also pay attention. Well, this is my personal opinion.
Another issue, okay, maybe should try more attention, all yours attention. So we usually do is no matter you do is more physics oriented, chemistry oriented, maybe like means mechanical behavior oriented research. So in our research, in my half is life, maybe most of life is research, I really believe with the model I developed. Okay, we think that is always true, because based on some assumption, we say I love the formula I developed, I derived. Okay, so I want to try my best to argue my model is correct, my theory is correct. So in that sense, that means I'm very biased my model. But from the data science point of view, that is not this issue. The data is machine learning, as I mentioned here. They're assuming there's a big assumption. They are assuming the true correlation is not available. All you can find is optimal approximate is a formula, a correlation. No matter it's analytic or non-analytic. Okay, that is the approach somehow are different. Okay, so now we are all working in this area. We have to pay more attention to this issue.
Okay, so now I think it's time for the next talk. So let's thank Professor Zhang again. So let's move on to the next talk. It will be given by Markus from Berlin. I think he's going to talk about NOMAD, which is a big data platform. So Markus, please share your screen and start.
Yes, hi, good morning. Yeah, thanks for the introduction. I hope you can all hear me well. I also hope that you can see the slides properly.
Yes, I can see and hear.
Okay, great.
Yeah, please.
And just to confirm, I have 45 minutes to talk, right?
Yes, yes.
Okay.
Including discussion.
Okay,
and we have a
okay.
30 minutes discussion at the end of this session. So,
yeah, that makes sense.
Yeah.
Okay, thank you very much. Yeah, yeah, thanks for inviting me. Yeah, I'm here to present NOMAD, which we call a fair data sharing platform for material science. And yeah, material science, those of you that know NOMAD, you know that it has a very strong focus on electronic structure simulation data. But this is also why I wanted to talk about FAIR-MAT. And FAIR-MAT is an NFDI consortia. In fact, we are starting with tomorrow. Tomorrow is our official start date for this project. And the goal of FAIR-MAT is to bring data sharing to a wider material science community. And this is where we want to use our NOMAD software, our experience that we take from DFT simulations, electronic structure codes, and offer this to the whole community of condensed matter physics. So, yeah, I will start a little bit with like a high-level overview, talking a little bit about what NOMAD actually is. For those of you that don't know it, and then I want to also do the same thing on FAIR-MAT. And then I want to go a little bit more technical and explain to you how NOMAD does work internally, what architecture we use, how it's operated, how does it work, how could you extend it or use it for yourself, all these kind of aspects. And then hopefully in the second part, I concentrate more on an idea that's the NOMAD Oasis, which is the idea that you can use NOMAD also locally in your institutes. And this is all what we want to use in FAIR-MAT mostly, to build really a federated network, a federated data sharing network where everybody can participate and we basically distribute the data over the globe and thereby making it fair and accessible to everybody. Yeah, so that's the plan for today. So yeah, let me start to hop in and talk a little bit about what NOMAD is. So we characterize NOMAD as a fair data sharing platform for material science. And here we have two parts. The first part is the data sharing. And we think that data sharing means, and this is in contrast to many other material science databases that you might know, that we are not hosting our own data, right? We are really there to share the data that others provide to us. So the goal is to make your data, the data of the regular researchers, available to others. So that's the fundamental thing of our platform. And the other part is the material science part. And this means, and this is also in contrast to other platforms, like where you are more about generic data sharing, when you think about Zenodo or when you think about Google Data Search or these kind of things. What we want to do is really to be domain specific. We want to extract rich domain specific metadata from the files or from the data that is provided to us. So it's not just about identifying the author and the title and abstract and stuff like this. It's really about digging into the data and finding out what are the specifics. What is the chemistry? What is the concrete crystal system, the structure, whatever that was measured or simulated? What are the parameters used? What are the material properties that were calculated or that were like gained by any other means? And currently, NOMAD is mostly about ab initio calculations. But of course, and this is where FAIR-MAT comes in. We want to extend this. We want to also open this up to experimental data, to data from synthesis, from data on different scales of computational material science and so on. Yeah, and NOMAD, in NOMAD, all the data is visualized. It can be downloaded, it can be browsed. We have like a search interface. It can be browsed in a common format with a common schema. It has a graphic user interface. It has an API so that you can work with the data programmatically. I have a few screenshots here. The first thing that you see is like our search interface, for example, and then you see like the visualizations, the overview that we have for all the data in there. Then it really depends on what data is about, right? To really see different charts with different properties on it. We also have like this detailed view, the archive, where you can really see all the different numbers and data points that we identified in the data that were provided to us. This is what like later we will talk about a lot about the archive and how it works. And we also have like an analytics platform, like Jupyter notebooks that are run directly on our servers that you can use to access the data and to do some analysis on it. And then there's the whole data providing part, right? So it's a publishing platform. It's really about like people giving us their data or share the data through the NOMAD platform. And we allow everybody to have a simple process of uploading their data. It's completely free. Everybody can publish their data. You can have an embargo on your data, to assist the publishing process. You can get a DOI on your data for your papers for referencing. And then you can share your data with either in private with reviewers, for example, or with colleagues, or like publicly with everybody. Yeah, that's the whole idea about NOMAD, right? To summarize it a little bit, you could say that NOMAD is there to assist the overall research process. You basically want to do the same thing that the publishing world is doing to papers, we want to do for data, right? So we want to enable everybody to publish their data.
Your audio is currently stopped, at least in our place. I'm not sure.
Okay, let me check.
We're back. We're back.
Okay. I hope there will be no more interruptions. I have no idea if this was on my side. Yeah, we will see. Let me know if anybody else can't hear me. Just let me know. So yeah, basically we want to do like the publishing game, but with data, right? So it starts with data on your hard drive, and then we allow you to upload your data, and then we allow you to publish your data, and then you publish data that everybody can see, that everybody can explore through our search interface, that everybody can have a look at and see visualizations of data. And then of course you can analyze the data with services that we provide. And then the cycle closes, right? So you get inspired by other people's data. You want to reproduce their findings, or you want to do similar analysis or do similar experiments or whatever. Then we are back to you and the data on your hard drive, and the circle begins again. So that's like the overall picture, like having NOMAD as a set of central services, like a web page that you can go through and that you can put your data to, that you can also use to see what others have put up there. And then there's this other idea that I briefly mentioned in the beginning. We could also allow people to use the NOMAD software, locally and have their own NOMAD, right? Why not? NOMAD is just a piece of software in the sense that we run on our central servers, but in principle, everybody could run it. And this is what we like to call the NOMAD oasis. And here the same thing applies, but you have like shorter cycles, right? You can upload data to your own NOMAD. You can share it with your colleagues in your institute. And then, of course, at some point you can say, okay, my data is ready now. I want to publish it and move it to the central NOMAD. But even with your local NOMAD, you can do the same things. You can use the search interface to explore the data that's available at your institute, that your PhD students were putting in or whatsoever. So the idea is like you never really lose the data of some PhD student left your institute or that left your group or something like this. And of course, you can use all the analysis tools that we have. Yeah, so that's the other big idea. Like besides having like this overall publishing, we really want to make NOMAD available for your daily work, right? Have it at your local institute and really use it to manage your data. So it's not just about publishing it after the fact, after you're done, and basically you're just about like to write a paper and then publish it. But even in between, for all the intermediate results, it might be a good platform or a good useful platform for you to just manage your data. And this slide, I wanted to highlight a little bit that NOMAD is not alone, but it's a large ecosystem of similar projects or related projects that fulfill like different tasks or that have different focuses in this whole thing. I put NOMAD in the center. You don't really have to read everything. I try to highlight a few things where we differentiate from our colleagues. So one set of very similar things are all the big databases that you know, like something like Materials Project or the Aflow library, stuff like this. They have like these high throughput workflows that constantly produce new data, and then that they show with a web application, right? So they also have like a search interface usually, and you can see the data and download the data and do something with it. The big differentiator, of course, is that NOMAD tries to be a platform where everybody can put their data. It's not just about our own data, and this comes like with unique challenges, right? When it comes to like curating the data and taking care of data quality and stuff like this. Then, of course, there's this whole realm of having methods that provide data, right? Having electronic structure codes that allow you to do simulations, having workflows that allow you to do lots of simulations at the same time, but also look at other branches of material science like instruments and electronic lab notebooks and stuff like this. Like there's the huge amount of projects that produce data, and with these projects also there's a huge amount of data formats that need to be supported. We will talk about like data formats and how to convert them and how to find metadata later in the talk. And then there's this whole other side of databases when you think about having just general databases or having something like Zenodo where you can share any data, right? These very generic platforms that allow you to basically put up data, get a DOI, put it in your paper, and then others can download it, which is fine, but it has like on the negative side, it's really hard to identify data in order to find the exact data that you want. Like if you ever try to use Google data search and try to find like a simulation for a specific system that you're interested in or for a specific material, it's not easy to find anything in there because like the only thing that Google indexes is like the titles of people that gave people the data sets and stuff like this. And then, of course, we have all the research networks like the Deutsche Forschungsnetzwerk or the European Open Science Cloud or these kind of things, which are more like political initiatives, but where it's all about like connecting the dots and having databases interact with each other. And this is where FAIR-MAT plays more like an important role for us, where we want to use the NOMAD software to build like a larger network of connected repositories and also connect to other repositories out there. Yeah, so that's the, and yeah, one last thing I wanted to mention is standards, right? Data formats, of course, are tried to be standardized when you think about something like Nexus that you might have heard of. But there might also be in the future be standards for like larger schema efforts for like having joint ontologies like the the MO for material science, for example. And then there are API standards. One thing that a lot of us are working on is the Optimate standard, for having like a specific standard for an API that allows you to connect to material science databases in a common way, so that it's easier for you to use multiple databases at the same time. And this also makes it easier for projects like FAIR-DI, for example, to connect databases, because like, it's much easier to get data in a consistent form, to retrieve data or search for data in a consistent form. Okay, that's what I wanted to say about like, the related work and the related stuff. Some of it will come up later again. Let's continue with talking a little bit, or first summarizing a little bit NOMAD, and then seeing how it plays into the whole FAIR-DI idea, or what FAIR-DI actually is all about. Yeah, so just to summarize, like NOMAD at the moment is a set of central services. There's a website you can go to, and then you can basically do all the stuff. You can take your computational material science data, zip it up, and just upload it to NOMAD, publish it. And then others can see what you have published, right? There's a search interface, and then there's means to visualize and analyze the data. And the source software package, in principle, could also be run on different servers, right? That's the whole NOMAD Oasis idea. And this is what we want to do with FAIR-DI. Yeah. And the reason is like NOMAD is like already a long-running project, and we have like quite some experience with dealing with metadata. And even though it's like focused on a specific domain of material science, but we really want to bring this experience then also to the other domains. Right? So NOMAD was like a little bit of history. NOMAD was created like almost like 7 years ago. And by now we are accumulated like over 11 million code runs that were basically published on NOMAD. We have like over 100 terabytes of raw data. That's like all simulation input and output files. And if you calculate all the different quantities that are in there, like all the systems that go in there, all the elements that go in there, all the energies that are calculated, and everything, you come up to like over 7 billion little pieces of information that are in the database. We support over 40 community codes, so almost all electronic structure codes you might find are supported by NOMAD. And all the data that we have is made up or was provided from over 400 researchers from all over the world, including 3 of the large high throughput databases, OQM, Diaflow, and the Materials project. Around 250 users daily reach our website and use our service in some capacity. Yeah, and now in FAIR-DI, we basically want to do the same thing, just on a larger scale. We want to use the NOMAD software. We want to still have like a central kind of installation. But now that we are looking into like different kinds of material science, it might not work this way in all cases. Like, for example, we imagine that we have institutes that run experiments that produce like a large amount of data. Data that's so large, like when it goes in the terabyte or petabyte regions, where a centralized idea isn't just working anymore, right? And we really need local repositories, or the institutes really have to take care of their own data. And this is where the idea of the Oasis comes in, right? So people, institutes could run NOMAD software in their own institutes, and then we just have a connection to the central system, right? And the central system then more acts as a central search index, so to speak, like the Google for material science. So we only transfer some of the data, we only transfer the metadata to the central system, and thereby allowing to publish the data, or at least publishing references to the data, while the data stays at the local institute. But the central installation will then make the connections that allow people to reach the different installations. And then we have to accommodate like certain different scenarios that we might expect. So other institutes might have like a different thing where they already have like existing data infrastructures, they already have existing repositories or ways of means of managing the data. But we still think that the Oasis can be an important role, and then basically be put on top of it as an interface, basically, to allow the connection to the central servers. Or we might have institutes that run like larger laboratories where lots of instruments need to be connected, where electronic lab notebooks come into play. In essence, just a different source of data. And again, we think that we can use the NOMAD software as a local repository But there might also be institutes that say, okay, the NOMAD oasis isn't really working for us. We need like a different set of features. But then still through API standards and stuff like this, we are striving to make a connection and to allow to index this data on our central installation. Yeah, that's like the overall idea. We really want to build like this network of repositories. And in order to do this, there are like certain tasks and challenges that we have to address. Like the biggest one, or one of the biggest one, and I think that was also discussed here at this workshop in some detail, is like metadata. How to define the metadata, how to align the metadata, right? Different methods mean different metadata, but somehow it has to put together. So that's one big part of the FAIR-MAT project, dealing with metadata. Then, of course, all these repositories have to be established, right? The NOMAD software has to be further developed. It has to be adapted to this OASIS use case, and then we really have to build these local repositories. Another big challenge. And in FAIR-MAT, we basically have 5 bigger experimental methods on board, or institutes that represent these methods. This is basically what we want to start with, and then lead by example, and then hopefully connect to more and more institutes and to connect to more and more different methods. By the way, do you see the map of Germany in the background? That's just because, like, at the moment, NFDI is like funded by Germany, but of course, all these ideas should apply to the whole world. And yeah, another thing is like the central thing, right, which we in the context of FAIR-MAT like to call the portal, and this is where all the data becomes fair in a sense, right? This is what makes data findable, what makes data accessible. That's the central gateway that everybody goes to actually reach the data that might then be stored in different repositories. And then, of course, there's lots of efforts when it comes to connecting everything. Like, you really have to see this as a connected network, and not an isolated network, right? And then there's also efforts to connect this to like larger research networks, like the Deutsche Forschungsnetzwerk or the European Open Science Cloud. And of course others as well. And then another big point in this whole FAIR-MAT thing is like electronic notebooks and laboratory information systems, like local IT infrastructures that already connect laboratories and the different tools and instruments that are used there into each other, which is like yeah, on a local scale, very important for us to integrate the data already and provide metadata in a sensible way, so that it's not just about like singular measurements, but really about like whole experiments and workflows and stuff like this. Yeah, this is a little bit what we plan for the FAIR-MAT project, or what the different focus areas are, and how the overall architecture that we envision should look like. And for us, the important thing is to really have this like a connected network and reach out to the community and basically make people work together and yeah, build this network together in order to have to finally have a way to really make the data reproducible, to really share the data, and not just having papers where we write about your data, but really make your data available and make others help others use the data. Okay, that was my high-level overview about everything. I took quite some time on this, but I think it's important that you get the picture. I will increase now a little bit in speed to get some of the technical ideas out. Yeah, how does NOMAD work from a user's perspective, right? Yeah, it starts all with the files that you have on your computers. Like, imagine that you have done a few vast DFT calculations, for example, and you want to publish them. Typically, what our users can do is they just take all the files that they have as they are, they just put them into a zip archive or into a tar file, and then they just upload it to NOMAD. And then on our sides, we basically extract the archive. We go through everything that you provided, all the files that they are there, and we just try to look for files that we recognize. And this is what we call the main files, right? For each file that we recognize, for example, the VAST1 XML, or something like this, will then represent a new entry in NOMAD. And then that entry might consist of more files, but it's the one is the main file, and then you have like auxiliary files or your input files or other files that you generated or files that you just put into the same directory. This is what we call auxiliary files. And then we put our parsers on the main file, Like for each of the different codes that we support, we have basically a parser, and then the parser digs into the file and tries to find all the information and to very fine detail. And then it transforms this information, this data and metadata, into a common format that we call the archive. So each entry will get one archive, and this archive provides all the information about the applied method, the studied system, the calculated properties, and more, and everything under a common scheme and the common format. Entries for similar systems are then aggregated into materials, and this is what we call the NOMAD encyclopedia, where we basically collect entries that are simulations that were done for the same material and provide them in a way that you can see, okay, for this material, these and these kind of information were put together. And all the data, all the raw files that were provided, the archives, the entries, and the material data is all available through our user interface, but there's also like an API that you can use to work with this data programmatically. And we also provide a Python library that you can use to like easily use this API to get the data and extract certain archive parts that you like for analysis, for example, in your local Python environment, or you use our analytics toolkit where you can run the Python directly on our servers. Let's talk a little bit about the archives. So, because these are really important for us, the NOMAD archives, our common file format is the basis for everything. It provides the necessary metadata for our search system, for our representation and visualization in graphic user interface, for the encyclopedia, and also for analysis. This is what the typical archive looks like in our user interface. The archive is basically a structured format. It's hierarchical. Everything is structured into sections. Sections can have subsections. It's like a book, basically. And then sections can also contain quantities, right? Like the actual data. So in this example, for example, we see like a typical archive for a simulation run. So we have something like this section run, and then the section run is subdivided into a section method where everything about the method goes, a section calculation where the calculation results are going, and a section system that describes the system that was simulated. And then in this example, if we dove into the system, and you see all the quantities that make up the system, like all the site positions and the atoms there, and what the lattice is, and all these kind of things. So you see some visualization of the system here, and then I highlighted the lattice vectors, and you see like a mathematical representation of what the lattice vectors typically look like a 3x3 matrix and stuff like this. So this is like our archive. Like we really try to dissect all the information and provide it in this hierarchical form. Let me skip this a little bit. I think you're all pretty much familiar with this, what data and data schemas and metadata are. Let's talk a little bit more about like how to homogenize like heterogeneous data or metadata. I use like different colors and different symbols here to represent different things. So when you look at a structured metadata file, for example, there are two things to consider. One is like the information inside that might be heterogeneous. One method like really produces completely different information from another method. Like a microscopy picture is a completely different thing from a DFT calculation. And then another thing, this is what I want to represent with the symbols. And then another thing is the colors, because like the data format, right? JSON is different from HD5, and then ASCII is different from XML and these kind of things, right? And these can be considered like separately. Converting the data format is usually the easier task, right? Because you basically keep the same information structure, you just change the underlying bit-by-bit representation of the data. So getting rid of the colors usually is not that big of a problem, right? It usually needs a converter or parser of some sort to read the information and just write it into a different format. But the more challenging part is to deal with the differences in information, right? How can you align like a microscopy picture with a DFT calculation? How do you identify what's similar in them? What is like joint information and what is like completely disjoint information? And usually in material science, it's the material that makes the connection, right? Or one of the aspects that can make the connection. And this is like where the challenge then really begins when it comes to defining metadata, to finding schemas that work for multiple methods, or at least that have parts that work for multiple methods. This is also where ontologies come in order to make sense of all the data, and so on and so forth. Yeah, so in essence, in order to combine data and make it available in a common platform or in a shared platform, we have to get rid of the data format, like we have to get rid of the color, and then we at least have to integrate different symbols, right? And find ways to find like these hierarchies that then allow you to represent information in a common hierarchy, even though that information might be different. And in NOMAD, it works a little bit like this. We have our parsers that go for different file formats and try to convert this into an archive. I wrote this here in blue, like all the blue parts coming directly from the parser. Let's say if a parser looked at the simulation, it produces like this section 1, which then contains the data about the simulation. If it tries to parse like the data that comes from experiments, for example, like a measurement of some sort, it produces a completely different hierarchy of information. But then we have another part, and this is where we try to join the pieces of information. That's the red part here. That's our results section, where we basically try to identify, okay, what is the material that was simulated, or what is the material that was observed with the measurement, and extract this information into a common place. And also have a common place where we try to structure all the method information that went into this. So even though that we are talking about different methods, like a DFT calculation, completely different from like taking a microscopy picture, for example, but there are still similarities when you think in terms of hierarchies, right? You have a DFT calculation on one side, but you might have a molecular dynamics simulation on the other side. They're different methods and they might produce different metadata, but there are also some common metadata. For example, for both of them, you use a computer program to do the simulation, right? So the program name, the program version, maybe the operating system or some numeric parameters might be the same or might share some metadata. And this is what we try to do with these hierarchies, like put the more common information more on top and the more detailed information more on the bottom, and then somehow make this available through a search interface so that you can really select, like either you are on the top level, you're just interested in materials, you want to see everything for a material, or you want to dive deep and go to certain methods and then filter based on certain criteria that these methods offer. Let's say for you are looking for a certain DFT code or for a certain functionality that is used or something like this. Okay, let me skip this very technical stuff. Maybe a few words on our architecture. We try to make the whole NOMAD thing as coherent as possible. So we have like one large source space. We try to use as less tools as are feasible. So everything is based on Python. We use just one framework for doing the API. We have a processing framework. And then we have like lots and lots of these parsers, of course, but everything is connected with one source code project, and then we generate one Docker image from this project and one Python package from this project. And then the Docker image is what we use to operate the system. But everything is like together. It's not like 20 services that are then operated independently. It's basically one image that you have to spin up in your environment, and then you can basically start NOMAD. There are a few databases attached and stuff like this. But we try to make it as simple as possible to foster the idea that others might also be able to install this and run this. And we are at a point where we have like a very short tutorial on what's necessary to run NOMAD. And we have like the first 5 institutes that are now running in this. That we're able to deal with this. So it's just physicists that are able to run this software and maintain it locally and have these oases run. Yeah, that's sort of like the core idea about the architecture that I want to convey here in the little time that I have. And let's go on and talk a little bit more about the oases and different use cases that we have for oases. So I talked about the oases quite a lot already, right? So I think I understand that this is the idea of having NOMAD at your local institute. But why would you do this? What are like typical use case scenarios for this? So we have the NOMAD software, and it can run in different scenarios. The most important scenario for us is of course our central installation, where we basically have a huge amount of public data, then some private data, embargo data that's not yet published. And we have our central user management and stuff like this one. But then, of course, there are different things that you could also use the software for. For example, you just want to manage your data locally, right? You don't want to publish it yet. You just want to manage it locally. And once you think your data is ready, then you want to publish it and push it to the central system. This is what you might call the academic oasis. Then we have other scenarios where you want to build a NOMAD mirror. just because, like, I don't know, you are in a far distant country, and the connections isn't always this what you want to have. And if you want to have like larger amounts of data available, maybe you want to build a local mirror of NOMAD. That might be another use case. So basically you take all the public data and mirror it. Then we have the industry oasis, like let's say industry wants to do like large scale analysis on all the data that we have using artificial intelligence and stuff like this. But of course, industry is industry, and they don't really want to see anybody what they are doing. So they don't really want to use the central NOMAD. They rather use a mirror of all the public data, but then also manage their local data, of course, use their own local user management. So really don't have any connection to the internet at all, and just run the oasis in private. And then, of course, we have the FAIR-MAT oasis. This is like what we want to do in FAIR-MAT, where we have like each institute is run its own NOMAD, and then they work on the data locally, either public or private. It really depends on the use case. But some of the data they want to make public, right? So mostly the metadata for their experiments and stuff like this, they want to make public and transfer to the central NOMAD, while the larger part of the data remains in the repositories. Yeah, so these are the common use cases for the NOMAD oasis. And now it's basically up to us to make the software as flexible as possible to foster all these use cases. And we already made the first steps, and it's now installable in a pretty easy fashion. And then we also can make a connection to the central NOMAD, like on your oasis. If you have some data, you can press a button, and it's automatically going through the internet into the city system. It's not right. I have more slides, but for some reason they don't show up. But maybe my time is already up, and maybe it's a good point in time to stop here. Yeah, so I think in summary, I showed you a little bit what NOMAD is, how it works internally a little bit, and I also talked about this FAIR-MAT idea and how we want to use NOMAD to connect like multiple institutes to each other. And the core ideas are that we really want to have like this domain specificity. We are deliberately chosen this bottom-up approach where we use parsers to dissect different data formats and then try to homogenize it after the fact, because we believe this works much better than to just try to dictate data formats to everybody, which usually doesn't really work. That's one key aspect. And another key aspect is that we really want to build this network, because we believe, okay, data is really big. Especially when you look in experiments and certain methods there, you can't have just one server where you try to put all your data. It doesn't really work. You really have to build this network. But of course, there has to be fair. You have to be able to find it everywhere. And this is what we want to achieve with this central portal, or the whole FAIR-MAT idea, where we use one central metadata repository, basically, in order to allow the search and then access the data in different installations. Yeah, okay. Yeah, thank you very much. Let me end with this picture here. Hopefully it will inspire a few questions. Yeah, thank you again for listening.
Okay, thank you. Thanks, Markus. So are there any questions about a NOMAD and a FAIR-MAT?
I have one question here in Louvain.
Yeah, hello.
Please.
I have a very general question, because as you mentioned, NOMAD has been around for quite a while, and you listed how many people visit the website and so on. So is there any data on how useful things turn out to be? I mean, are there new breakthroughs, papers? Is there some statistics on the actual effect of NOMAD in this particular case?
I think that this is very difficult to achieve. I know what you mean, and it certainly will be necessary in the future to actually demonstrate that this really works and has an effect. But of course, the questions arise: how do you do this, right? One thing that we try to do, even though they are not yet really public statistics about it, is to track the references of the DOIs that people create with NOMAD, right? So what people can do when they uploaded the data, they can create data sets and have a DOI for this. And in principle, you could do the Google Scholar thing and try to look where these DOIs were actually used, how many publications are there with data in NOMAD. But this does not really tell us really how much this was used. But then you really have to look at the citations to make sense of this. That's one way to go about it, right? To go through publications and try to find something there. Otherwise, we only have like statistics on how many people are using this, right? We can look at our servers and see how many people are requesting something, how many people are downloading something. But then we only make assumptions about what they might do with it, right? And how successful they might be with it. Yeah, but that's the ideas that we have in this regard. At some point, we really want to have these statistics and also make them published, publicly available. Yeah, but that's what I can say to this question, I guess. Maybe you have better ideas on how to do this, how to actually track the usage of a database, and not just how it was used, but also how much was the impact that was generated from this.
I definitely don't have better ideas, but I was, because you say DOE here, so. But sometimes people use, say, 100,000 data points, right, from all over the place in artificial intelligence. And so I don't think that's going to be referenced in any paper. Yeah. So a lot of this will be hidden.
Yeah, but this is another thing that we want to enable, right? We want to also enable people to create data sets for data that they use in analysis, right? So when we think about data sets, so the data set isn't really the data you uploaded. The data set is really, you can look at the data that's there and you can create a data set from this, right? It's like a tag or a label or like an album or whatever. And then you can make reference to this. So in principle, you could write a paper and reference like a set of data that you use for analysis instead of just referencing your own data.
Okay, thank you.
Yeah. I can read some questions from the chat if you like.
Yeah, and there is also some raised hands, so you can start from the chat maybe.
Maybe we start with the raised hands because I get the feeling they are directed towards the last question.
Then it's Matthias.
Actually, mine is related to the last question because it would be really great in measuring the impact, but of course, a lot of the impact is that people look what is there and then they don't have to redo the calculation again. And of course, I mean, that will never be cited. And you said actually some people may just use the data and do it for use it for artificial intelligence. They should cite it, but very often they will not. So any ideas how to measure impact from the broader audience would be really great, and we like really to do that if you give us really an idea, but it should be of course not too restrictive, right? I mean, you still actually like to keep the privacy of people. So any ideas from anyone in this group here would be actually great to learn.
Claudia?
Yeah, I actually wanted to say exactly the same. So if I see how my group, for instance, is using the data, they just avoid doing calculations again, or they use input files and check outputs if they get the same results and so. So I think there's a lot of impact which we cannot measure. So I think it's just along the lines what Matthias just said.
So then I would continue with the chat if it's fine, or is there more?
There's still one question. There's one question here in Louvain from Mickey.
Okay.
Thank you very much. I have one question about maybe the inner working in NOMAD. Do you have any projects or developments going on where you try to put links between entries? For instance, if you would say, this entry is a structure that is basically a supercell of this structure with this kind of defect, or this calculation seems to be an interface between this material and that material.
Yeah, so I mean, there are a number of things I could mention in this direction. Like one is the encyclopedia itself, which makes the connection based on the material. And at the moment, this is like very simple, where we basically just create, where we say, okay, if it's the same letters in a similar letters with the same symmetry and stuff like this, and we say, okay, this is like it's the same material and make connections like this. This of course wouldn't catch like text stuff like this. Another thing that I could say is that we at least try to make most of the metadata that's relevant for these kind of questions available through the search interface, and you could try to make these connections for yourself if you're really interested. Let's say you have a structure that has a certain defects, and you also know the normal, the idealized whatever structure that would fit the defect. You could basically search for both and try to make the connection. In the encyclopedia, we have a few ways to do automated, no, maybe not, let's not go there. Then the last thing I wanted to say is like workflows is like a big driver for connections that we actually try to formalize. That's a key point currently in our development. We are looking at various workflow engines and try to gather the information that they saw about the workflow in order to make a connection there. So that let's say you do like an elastic constants kind of thing where you use like various DFT calculations together to compute elastic constants, for example, that you can really see, okay, these were the calculations that went into this, or like phonons are another thing. Or so we currently have support like for certain specific workflow codes, like PhonoPy, for example. But we really want to broaden this to the more generic approaches where you use like a workflow engine like Fireworks or ASE, ASR, these kind of things, and help users to persist the connections that they have between the data points in NOMAD. And this also for the whole FAIR-MAT thing, very important. There are other questions in the chat that go in this direction. How do you add, how you allow users to add their own piece of information, right? So our parsers only detect what's in there, what's in the VAST calculation, for example, but they have a really hard time in detecting why you are doing the VAST calculation and how it is connected to other calculations, and really want to they enable the user to basically provide these links for us, so to make it easier. But this is also then, like, besides technical challenges, also is like this cultural impact, because when people really have to spend some time and some effort in actually curating the data and going the extra mile to provide more metadata than just what we can discover automatically.
Yeah, I think this is a very important point to try to make these connections. And I think maybe the big success here is that people can just upload data without doing too much work, right? So I think if your amount of data starts growing, and there would be some automated processes to try to automatically find, just based on the structures, these kind of connections, I think that would greatly enhance the usefulness of the results in the database.
I think workflows can be like a short-term kind of thing to attack this, and in the longer term, like artificial intelligence, ontologies, all these kind of more miracle machines might have some potential to help us there to do these automated connections. And of course, these are all technologies that we look into.
So I just wanted to add to the question that a little bit of that is there already. So we are looking, for example, for similarities. So Claudia's group has really a concept that you'd say, actually, I would like to really have materials which have a similar density of states as this one, and then you get really the results. And so in the encyclopedia and in the artificial toolkit, we are exactly really developing these things to find similar properties, which at the end you then really will result in materials which you could actually combine even.
Yeah, that was the point that I wasn't daring to dive into, because it's more complicated if you want to look at it in detail. Yeah, but yes, this is like one example project where we are trying to do. And on a technical level, I mean, there's also like other initiatives that we have where we want to look into these sort descriptors for structures, and this way it's really more about machine learning and things to make connections. And yeah. I feel like there's in any case, there's like a great potential for future work and research in these areas. And this is also what we want to enable with something like NOMAD, like making the data available would be the first step for people to find new mechanisms and new methods to make these connections.
Maybe you can take the two questions that are in the chat, Markus.
Yeah, Andreas Pönicke is asking if the decentralized approach of NOMAD Oasis, how does it achieve persistence of the data? So I think the idea is that many research institutes have a hard time to deal with this on their own when it really comes to long-term persistence and storing stuff for like forever, basically. And how we want to do this in this centralized architecture, in this federated architecture, sorry. So yeah, the idea is that we think of the available data as a pyramid, and in this pyramid you have like more useful data and less useful data. Typically, you produce large amounts of data that you typically then just throw away, right? You were just doing experiments that is just garbage data that came out. Then along the research process, you refine your data more and more, and lots of it is like filtering, right? And then the data becomes more and more valuable along the road. Let's say you've done lots of pictures and identified those pictures that actually gave you some clean data, and then from there you start further analysis, and then you provide like a more condensed version of this, and so on and so forth. And at the very top, you have like this nice picture that you put in your paper, right? This is like how typically it works. And the idea is like when we are limited in what we can actually preserve in a long time, just because the size is super large and whatnot, we want to facilitate these pyramids and say, okay, for the very top, for the published data, for the high quality data, this is where we can offer something. And this is then where you just want to centralize data and put it into a central system that's hosted by research and by HPC centers and data centers that know what they're doing, and then have the long-term persistence there. So there might be 2 or 3 mirrors of the central node that are capable of taking some amount of data from the various institutes, so that we can at least store or at least have long-term persistence for published data or for high-quality data. How much of the pyramid we can store then really depends on how much data is there, how the just network technology, storage technology, and so on develop over the years. I hope that answers the questions at least a little bit. Yeah, the short answer, of course, is we can't really store all data and have like long-term persistence for everything. We're just producing too much. I mean, there are instruments that are producing like terabytes per second, where you basically need special storage structures just to keep the data for a couple of seconds, and then you have to throw them away because it's just too much information coming out of the sensors. So there has to be some clipping at some point, and you have to make decisions on what's valuable and what's not. There's another question from Matthew Evans. Yeah, for computational data, we have well-defined inputs and outputs, but for experimental data, the outputs from an instrument where we typically have no knowledge of the system, of the sample system or whatever, at least it's up to the user to manually enter this. Do you think parsers for existing electron notebooks is enough to capture the complexities of experimental inputs when it comes to constituents, materials, synthesis conditions, processing parameters, and so on and so forth? I think for this question, the workflow part is really valuable. And I think this is what ELNs will hopefully provide us with the connections, not so much the data itself, but the connections between different data points. If you think about that the sample came from somewhere, it was probably synthesized somewhere, and then you do some characteristics on the sample with certain measurements, and then you send the sample around and then use it here and there and so on and so forth. But the idea is like, if all the data is available and we find a good mechanism, for example, to identify samples, you could basically draw a history of the sample and see in what measurements it was used and so on and so forth. Thereby getting idea how the sample might have changed. I mean, that's another aspect where the sample might not, like some of the methods might be to some degree destructive or whatever. Then you get an idea of what the sample was, and you also make connections between all these measurements, and thereby might get an idea of what was actually measured, what was lying under the microscope, and so forth. On the other hand, it will greatly depend on user input, and as you mentioned, that's certainly a weak point, and the divergence from our NOMAD approach, where we do everything with parsers and stuff like this. You have to provide people with like manual input opportunities. Electronic notebooks are certainly the more common way to do this. And then the question is how to formalize these lab notebooks. Like some lab notebooks are really just notebooks, right? Where you just write down arbitrary text and it doesn't really help you. So one aspect of FAIR-DI is to develop like these laboratory information systems together with lab notebooks, so that you have like a tight integration between the various instruments, and then really have formal kind of metadata entry masks and forms and stuff like this, where you ask for certain information. But still, of course, you never know what the user enters in there, right? And how reliable this is. But again, as with all data in NOMAD, we just have to provide even more metadata to allow you to make assumptions about how reliable some information is. This is also a problem that we currently have with computational data, right? We have all this computational data in there, but we can't really tell people how good the data is. They have to discover this themselves, and we providing the metadata for this. Right? We say what the functions are, what the parameters are, and everything is there. And then you have to make a decision on your own how reliable this data might be. And maybe in the future, all kinds of ontologies and artificial intelligence might help you there. And then it's related to the other questions that we already answered a little bit. Yeah, I hope that helps you, Matthew.
Thank you, Marcus. Claudia, I saw that you lowered your hand. If it's not important, then maybe you can take a break, because otherwise it's going to be very short. It's okay? Okay. So we can reconvene in 22 minutes then. See you later. Thank you all.
Bye-bye. Thank you.
Yeah.
Sure. Can you see my slide and hear me correctly?
Yes, yeah, I can hear you and see your slides.
Great.
I think now it's time to start next session. So let's welcome Dr. Giovanni Pizzi from Lausanne, Switzerland. So he will talk about AiiDA, material cloud, and computational workflows. So please.
Thank you very much for the introduction, and thanks everybody. It's been a very interesting workshop up to now, and what I want to discuss today is two aspects actually. The first one is how in AiiDA and Materials Cloud we achieve fair data access and sharing. In particular, of course, focusing on the field of computational material science is what we do. And I would also add one more R actually to the R of FAIR, which is the R of reproducibility, which is something we push a lot with our infrastructure. But this will be probably the first third of my talk. But in the second part, I want to discuss how to push FAIR beyond the quotation mark just data. I want to discuss about how we can achieve FAIR simulations and fair access and sharing of codes and workflows. So let me start. Maybe just a comment. I tried to put at the top right here some FAIR letters. Some of them would be red sometimes. I'm trying to say which of the FAIR pillars I'm addressing mostly in that specific slide. Let me start with quickly introduction of the challenges we have when we want to run high throughput simulations in a HPC fashion. And the first one is workflow automation. We need to have the tools to be able to run and manage complex workflows with advanced error handling. As we know, the codes can crash, and we need to have a way to deal with those. And we'll discuss this later, how important this is. At the same time, of course, you don't need only the workflows themselves, but you also need to have an engine where the workflows can run in a robust way. And once you run all of this, you need to manage all the data which is produced, and not only to store it in an efficient way, but also to be able to query for it. And finally, an important point for us is the one of reproducibility. And the fact you store enough information in order to be able to fully reproduce any computational workflow. In order to address these challenges, we've been developing what we call the AiiDA platform, which is a computational science infrastructure for high throughput workflows with full data provenance. It's an open source Python code. You have here some links, which indeed provides a number of features, including a scalable workflow engine, automated tracking with the full data provenance. I'm going to discuss in a moment what this means for those of you who don't know. Has built-in support for HPC computation, so you can just submit simulation on HPC facility, and has a flexible plugin system. As I will show, we now have a support for over 100 different codes from material science mostly. So let me first start with the first part of the talk about fair data access and sharing, as opposed to fair simulation access and sharing, which we'll discuss later. The key aspect we started from in the core design of AiiDA is the idea that you really want to represent the full data provenance, the full history of any piece of data you have and you bring into life when you run simulations. And the way it's designed is very simple. You start from the concept that any calculation has a number of inputs and a number of outputs. This could be a crystal structure, some parameters, and some output structures, some output forces and stresses, etc. And now, if you imagine that any piece of data can be the input of another calculation, you end up with a structure which is that of a cyclic graph. where if you have a final result, let's say a band structure, you can easily just look at the graph and understand this structure, this band structure was generated by a given calculation with some parameters, and this the structure itself, the input crystal structure itself, was actually the output of another calculation, and all the inputs and all the outputs of any step going up to the very original structure, let's say, imported from some experimental, for instance, crystallographic database. And this graph just gives you the idea of the concept, but when you look at real provenance graphs as created by AiiDA, they look like this. So they are very easily quite complex, not because we represent things in a complex way, but it's really what we do as material scientists. When you run a molecular dynamics, maybe with a mixed method, DFT, mixed with some semi-classical method, you have to run a lot of runs, you have to do some pre-processing, prepare the structure, run some dynamics and so on. So the graph, which represents the inputs and the outputs of every calculation, becomes very quickly very complex. And the one in the bottom here is a graphical representation of an actual database with the calculation of basic electronic properties and binary functions of only, I would say, only quotation mark 500 materials. So it's not even a high throughput database. I would say it's a mid throughput, maybe, or mid to low throughput database. Still, the amount of connections you have in the database is already so large that it's essentially impossible to reconstruct a posteriori. And indeed, in this talk, I will try to also mention how we address some of the issues which have been touched upon in the final questions before the coffee break, how we can also infer by storing this graph the reason why certain calculations have been run. And so even the best willing scientist who has been running this will not be able to really reproduce in detail what has been done by just and describe it in a paper. You really need to have a tool like AiiDA that tracks this provenance while the simulation are run and keeps track of the full metadata, the full provenance information for any calculation. And once you have this, it becomes relatively easy, a posteriori in a sense, to look at this graph and understand what's happened and create any type of metadata format you want. And a few years ago, we already showed in practice how this could work in the case of integration of AiiDA with a theoretical crystallographic open database, the theoretical counterpart of the COD database. That defines the metadata format, and we were able to implement an automatic converter that, taken the AiiDA graph, was able to create all the theoretical metadata about the calculations. And since here we're speaking about FAIR data, the other important thing is also how to make it easy for others to reuse the data. And so AiiDA has features to export the full graph you have in your computer or parts of this graph, say maybe a subset of your calculations, and either share them with collaborators or upload them to public repositories. And one of them, which is the one we maintain and develop, is called Materials Cloud, which has specific features tailored toward AiiDA. And in this sense, what I want to show just in the next 3 slides is how combining the graphs automatically generated with AiiDA with the data sharing capabilities of Materials Cloud, you can really achieve FAIR data sharing. By the way, Materials Cloud is one of the GoFair implementation networks. So Materials Cloud has a number of sections, some of which are more geared toward data generation. What I will focus now on just the last 3 sections, Discover, Explore, and Archive, which are the one more relevant for the topic of FAIR data sharing. The first one I want to mention is the archive. Is something in a sense very similar to Zenodo. Is an archive where you can deposit files and data associated to a paper you've been produced. As you know, most funding agencies now require you to write a DMP and to publish also the data associated to your paper in a fair way. And Materials Cloud Archive uses the same actually backend called Invenio as Zenodo, and is, however, a curated and so actually moderated, I would say moderated and topical database. It's about only materials science, and it's moderated in the sense that any entry submit, it's open to the world, so any of you can submit here data associated with your papers if it's about material science. The moderation is not a scientific peer review. It's just a very lightweight process where one of our moderators will look at your entry and give positive suggestions in order to improve the quality of the data you're submitting. And actually, our experience, I would say, more than half of the entries require some request for feedback, but all authors typically get it in a very positive way, because requests could be things like, please don't use an Excel format, use maybe some more open format, maybe make sure this file is in another open format, it's clear, there's a README explaining what the data is about, etc. The archive is recommended by a number of journals already, like the Nature's Journal Scientific Data, and now also by the Open Research Europe journal. And when you publish data there, beside the user fields, authors, affiliations, etc., it also gives you a DOI to your data, and you can put data there which is going to be guaranteed to be there for the next 10 years. And now, if you also have data which is being generated through AiiDA, which is optional, in a sense, you can upload data here which are just files and without using AiiDA, but if you use AiiDA, you can very easily create new sections in the other two sections I was mentioning, Discover and Explore. And we'll just show very briefly with an example what this means, with the example of one of our studies, which is about discovering two-dimensional materials by simulations, by computational exfoliation. And since we did this with AiiDA, we created one Discover section, which is what our Discover sections are essentially project-based curated data sets. So that's a section about two-dimensional materials, where for every material, we have a list of computed properties and of interactive plots, so three-dimensional widgets to show the structure, interactive band structure plots, etc. But for any computed quantity, you have these little AiiDA icons. And when you click on them, you jump on the Explore section, which is essentially a browser for the full provenance graph. If you want, if you think AiiDA like Git, so Git keeps track of the history of your source code and AiiDA keeps track of the history of your simulation data, the Explore section plays the role of GitHub. It's a place where you can upload your Git repositories, or in this case, your AiiDA graphs, and you can graphically inspect them. And so in this specific case, let's say I want to know how the band structure of magnesium bromide was computed, I can just click here, and not only I see the band structure, but here on the right, I see a small portion of the provenance graph, which we're going to show live with a small video now, where the central node is your band structure itself, and you can see this was generated by this green square, which is a quantum espresso calculation. If you click on it on this provenance browser, you can inspect all the inputs and all the outputs of the calculation, not only the raw inputs, so if you're and you know how quantum espresso works, you will recognize it is a quantum espresso input and a quantum espresso output, but you see the full part of the subset of the graph where you see all the inputs and outputs of this calculation. And so, for instance, if you go to the input structure, you can visualize the structure, you can download the structure, but also you can also, again, discover what is the calculation that generated it. And you can go up in the history and discover, for instance, the input structure was generated by a quantum espresso variables calculation, and you can continue to go up and see all the parameters with which this structure was relaxed, and so on. So this kind of concludes the first part of my talk, which is about FAIR data sharing. I try to very quickly give you an idea why, by putting together the provenance capabilities of AiiDA and the visualization capabilities and sharing capabilities of Materials Cloud, you can achieve FAIR data sharing for computational data. But what I want to stress more in the next part of my talk is about how we can also have and try to achieve fair access and sharing for simulations. And as a kind of preliminary introduction, the first thing I want to stress, which is probably obvious, is that given a material, what we do when we do research is we typically compute relatively advanced quantities. We can start from basic ones, like a band structure in this example, but we very easily go to much more advanced properties. We can be the output of GW calculation, of molecular dynamics, and so on. And these are always the result of a relatively complex workflow, as I was mentioning before. Now, the AiiDA provenance graph, if you use AiiDA, is a very detailed description of how that specific piece of data came to existence and which parameters were used to generate it. So if you have it, if you want, it's like a log of what has happened in the past or what someone else has run. However, having workflows is one step beyond, because now you have, thanks to the workflow engine of AiiDA, which provides a flexible Python interface to run these workflows, you can not only have a description of what has been done by someone else, but you can run a new calculation on maybe another material or on the same material with different parameters using the same logic in a very simple way. the advantage of the workflow engine, which already provides out of the box a number of interesting features like robustness for connection drops to the supercomputer. And for instance, has a feature to allow to very easily implement error handlers, which are essentially functions which detect when a code crashes or has an issue and know how to fix the inputs and the outputs to make the calculation work. I will be describing this more in detail in a moment. Just to stress this, it's not that AiiDA provides the error handlers for any code. Every code workflow implementer will have to implement them, but AiiDA provides a framework to write these error handlers and make this very easy. And of course, there's another bonus. If you run workflows through AiiDA, not only you have the full automation of the workflow, but also automatically the provenance graph will be stored for you. Now, the first step to make this appealing and interesting for the community is that AiiDA should support a relatively large number of codes. And this, in a sense, is also about findability. What we've been doing since 2017 is to create on GitHub what we call the AiiDA plugin registry, which is a very lightweight registry where anybody who has been developing a plugin or a workflow or any kind of support for AiiDA can register it and just point to the GitHub repository of that code, the documentation, etc. Today, actually, in the past 5 years, we've been spending quite some effort to create a community around AiiDA. And as you see from the number of plugin packages in the past 5 years, it's been steadily growing from the very beginning when there were only 2 or 3, there were kind of Quantum Espresso and a couple more, to now where we have 66 different GitHub repositories providing different types of plugins with essentially 100 or more codes supported and more than 100 different workflows, which range from very basic ones to just take care of fixing and error handling of a code to relatively advanced ones for materials properties. Now, however, having a code is the first step. It's just the way to tell AiiDA how to generate the input files, how to parse the output files of a code, and maybe how to deal with workflows. But what we really want to go is to have some kind of turnkey solutions, turnkey workflows. And here we'll try to use some similar analogy to what Stefan did yesterday. So I'm making an analogy with cars. And if you have a car, say you want to drive your kids to school or you want to drive work, etc., you don't want to be an expert of an engine to know which pipes to connect to what, and you don't want to, if you change car, you want to have to learn again how to drive. You just want to be able to turn the key and drive. And in a sense, that's what we are trying to achieve with this idea of what I'm trying to mention about fair access to simulation. We really want to have something where I press a button and I get a reliable simulation. And this again is about robustness. So we don't want the engine to break. So in the same way, we don't want the calculation to break. But also we want to make it as simple as possible. As in cars, you still need a driving license. So you must still want to have a user running it, have some basic knowledge of what a crystal structure is, what a bond structure is, what properties are being computed, and what are the limitations of the methods we are using. But then we don't want to need, like in a car, if you want to change car and switch brand, you don't need to learn again how to drive, right? So the same way, it would be nice to have a way where if you've been using, I don't know, Siesta and you want to switch to VASP, you don't have to learn again how to run these simulations. And so trying to make this a bit more concrete in our domain, as a non-expert, and here, when I say non-expert, and I'm speaking, as you see here at the top, about accessibility of simulations, I'm speaking maybe of a computational, experimental scientist who want to have access to some simulation results, and maybe didn't do a PhD in simulations. So as a non-expert of simulations, I would like to be able to ask for something like this. I'd like to have the question of state, maybe run with this code, just because I have it maybe, or because I know it's better, I have a license for it, whatever reason, which I have on this supercomputer with given number of nodes. But I like that all the numerical parameters are automatically chosen for me, the basis set size, the k points, etc., to get converged results. And what I care in the end is I press a button, I wait for it to run, and I like to get some plot. And at the same time, however, and we show how this was a key design aspect for us. If now I have an expert user, a person with a PhD in simulations, I'd like to be able to understand which parameter we use, check them, and possibly adapt them as I want. Because of course, maybe the default parameters which are chosen here are not the one I want. And again, maybe one important thing, which maybe some people might ask, the goal of all of this is not to take out of the play, the simulation people, expert people in simulations. That's actually the opposite. if now the people experts in simulation can just help and discuss with experimentalists and focus on the science, we are essentially removing all the technicalities from it, of knowing if my simulation is a converged cutoff and things like this. Really, the goal of us as researchers should be really to focus on the science and not on the technicalities. And so if you want to make this possible, and in the next slide, I show what we implemented actually. There are, I think, three main challenges. One, we want to have these turnkey solutions, which involve a number of aspects. We involve robustness, so making sure we get a result, automatic error recovery, but also automatic parameter choice. The second aspect, as mentioned, is we want to get this balance between accessibility for non-experts, but with full control for experts, for instance, about parameter choice. And also would like to have interoperability among different engines. As I said, I'd like to be able to switch code because maybe I prefer to do something in a plain wave basis set for some reason and maybe a localized basis set for some other task, with same inputs and output formats without having to relearn everything. But as we learned very quickly, that is not any of these three is a large challenge. The largest challenge is to achieve all three of them at the same time. And so what did we do? Well, just a month ago, we published this paper, which is this demonstration of the implementation of common workflow interfaces to compute materials properties using 11 different quantum engines. That's an effort which started within the scope of the Max Center of Excellence, but actually very quickly was open to many more contributions. You see here all the code which are involved, some of them like CP2K, FLIR, Siesta, Quantum Espresso, etc. are part of Max, but many others are not. And as we show in a moment, everything we did is fully open, both the data generated, but also the code. So you can find the code here and you can look into the paper, which is mentioned here. What I will do in the next few slides, I will try to give you a sense of what we've been doing. So the idea in the end is the following. Let's say I want to compute an equational state for, say, aluminum with the Siesta code. Then now it's possible to just run this line. I just ask the AiiDA common workflows to launch an equational state with Siesta on the aluminum crystal structure, but here you can put any structure you want, with a precise protocol. So we have a choice of numerical parameters, which hopefully gives some kind of relatively high level of accuracy. And the important thing is now I can just change the string with any of the other 11 codes which were involved in the study, just press a button again, and the result that we get will be something like this, where hopefully everything matches, but I didn't have to tell the code which parameters to use. This is an actual figure from the paper. We'll be discussing the results in a moment. For now, I want to discuss a bit the philosophy behind it, and then I will show what the results are and what are the steps forward. So the first topic I mentioned is the automatic parameter determination. As you, of course, I guess, understand, and probably I think all of you had this experience, if you describe what you did in the supplementary material, the method section of a paper, it's in 99.9% of the cases not enough. I'm pretty sure all of you had this experience trying to reproduce a paper, reading there and not being able necessarily to reproduce everything. Because it's not because of even the best will of the author, there will always be little things you cannot write in a PDF text. Now, in order to determine these parameters, one option which we didn't do, which is quite complex, I think, is to define in a unique way all the possible parameters for any code. Say, if you define a cutoff, that's how it's called, that's how the units, and that's how you specify it. And then define a global best choice for any code. But now that's very tricky because of codes might have different basis sets, different organization methods, so this would be very tricky. So we went for a more practical approach. We just define these protocol strings. So essentially we say every code will have to implement a protocol called precise, a protocol called moderate, and so on. And what this means, it's up to the workflow implementer, to the code specific expert. With the requirement that when we then compare the results, at least to the precise protocol, results should match within a certain level of precision. And again, the name is just a kind of human readable name. And in our supplementary information, we try to give him kind of an expert should be able to read and understand and get a sense of what level of precision we are using. But as you will see, since this all run through AiiDA, you can go and check exactly every numerical parameter once the simulation is run. So that's the part about parameter determination. So every workflow decides some parameters. And as I can tell you at the beginning, when we started this, the first plot we got for the question of states, many of these plots were all over the place. But by iterative discussion together, we managed to align them and essentially to find robust choices of initial parameters. Now, our experience with running a lot of simulations also tells us that already choosing good initial parameters is key to robustness of a simulation. If you choose wrong parameters, the simulation might fail for a number of reasons. Already just choosing good ones helps. This, however, is not enough. If you run any DFT code, I would say with confidence, almost any DFT code, I'm sure you have a number of issues you might encounter. Some are relatively basic, like the wall time your supercomputer was reached, so you have to restart. But there may be a number of other things, like SCF is not converged, or metagonization method crashed, or the last SCF had a large pressure, you have to restart the relaxation, etc. And for each of them, an experienced researcher for that code knows how to fix that problem, how to change the parameter in most cases. And so this can be automated. And I stress this fixing of errors is very code specific. And so AiiDA, as I mentioned earlier, makes it easy to define handlers. We just decide error by error how to fix it, what inputs to change in order to try to achieve a converged result. Implementing it is up to each of these 11 or more plugin developers. And so the level of robustness of different codes we have might be different. Some might be much more advanced than others, but the good thing is it's very easy to add more. So if you discover there's a specific type of error failure, it's just a matter of adding one Python function to your workflow, which detects the error and will take care of it. Still, if you put together automatic parameters and robustness, it's already a lot of things, but it's not enough. Because still every code will have different ways of specifying the inputs, different output formats, different flows through which the workflow goes. And this is not easy for a person to switch. Just to give an example, that's a real graph from how relaxation in siesta in quantum espresso happens when it's run through AiiDA, or even when then it's used as a component of an equation of state. And you see then graphically the topology even of this graph is different. And so what we did, the last step, and that's why it's called common workflows, is we define a common format for the inputs and the outputs. We defined a very little set of mandatory inputs for a crystal structure relaxation. It was the first common workflow interface we defined. We just need to define the crystal structure itself, of course, a protocol string, the type of relaxation you want to do. Essentially, if you want to not move the atoms, just one SCF, or move just the atoms, just the cell, both atoms and cell, etc. And the engine. So which code on which computer you want to run with which CPU resources and wall time. We also standardize already a set of optional but standard metadata form inputs. So things like thresholds for forces and stresses, the electronic type, if you know it's an insulator or radio or not, it's a metal, etc. The spin type, if you want to use magnetic or non-magnetic systems. And in case you want to study an antiferromagnetic material, you can already specify in a common way for all these codes how to specify the initial magnetization per site. At the same time, we also standardize, of course, the output, because once you can run it, you also need to have a way to easily understand which simulations will run. So things like forces, stresses, total energy, relaxed structure at the end, and the total magnetization are all standardized. And one point to mention is that the total energy here is not standardized in the sense that it's the same total energy for all codes, but it's standardized in the sense that energy differences are well defined and define the forces on the atoms. Now, with this set of common inputs, as you see, it's quite limited, it's quite small, which means it achieves this aspect of having a relatively transparent interface. It's quite easy for a non-expert to run. You just pass a structure, you say, I want something precise on quantum espresso on the supercomputer. But as it seems here, naively, one could expect it's not good for experts. Because as an expert, I might want to change a lot of things here. I might want to use a different function. I might want to use LDA plus U or change some numerical parameters, etc. So a fully transparent interface seems to be not enough. And so let's say this graphical representation means if you have the common workflow, here let's say I didn't put any input, but let's say you might have only this common input. And this will call a number of sub workflows or specific executables with very code specific inputs. if I hide them from the caller, which is what I'm doing, I'm not asking the user to tell me how to specify the cutoff in a given code. This makes it very transparent, but also not suitable for experts. Now, if I look, the solution apparently to go to the opposite, which is to make it fully opaque in the sense that any input is exposed. So when I run this workflow, I can set any single input. However, as you can imagine, this makes it okay for an expert, but not good for a non-expert. And so what was a practical solution which came up with, a kind of technical design implementation, what was critical, is splitting the common workflows in two. So we have common inputs at the top. This we agree, we want them, and common outputs at the bottom. We also agree we want common outputs. But the way it's implemented is the following. The workflow, workchain is just a name in AiiDA for a workflow, is going to be code specific. So this could be a quantum espresso workchain to relax an atom. The only requirement it has is to produce the output in the common format, but the input can be anything it wants, can be very specific and very detailed. However, at the same time, the second requirement we have is that any of these workflows comes together with an input generator. And this time the input generator will take common inputs and will generate any output needed to be then directly passed through to the workflow. And so this kind of two-level design achieves what we call optional transparency. So a non-expert user would just use the tool as a black box, would just put the common inputs, take whatever their input generator generates, pass it to the Relax workchain, and then just look at the common outputs. But an expert user could just then, instead, an expert quantum espresso user or siesta user could then go in, look at this intermediate output and change them at will with anything they want. How does this look in code? So like I said, it's a Python, it's all this in Python. So you essentially just load with a factory the specific implementation. Let's say I want the siesta common workflow. You import the structure in a way which is the same for all codes. You can be from a file, from a zip file, it can be from a database, etc. Then you just specify, again, in a common format, which code you want to run, with how many nodes, and what is the workload time. And then you just call this input generator I was mentioning, take the outputs, and generate what we call a builder, essentially a wrapper around all the inputs where you pass the structure, the engines, and the protocol, and possibly the other optional inputs. Now, if you are a non-expert, you just submit it. If you're an expert, you go here, you add some lines to modify the inputs in the builder. Okay, this was the more technical side. I move on now toward the final part of my talk, where I kind of say what we do with this and what are the results. So what I showed you here is how to define common workflow interfaces to specific tasks. Here we focus, for instance, on crystal structure relaxation. However, once we have these common workflow interfaces to various implementations, one per code, now we unleash the power of it because we can now implement single workflows for advanced properties, which will be the very same code for any implementation. So what we already did, for instance, is implementation of equation of state of dissociation curves, because once you implement the concept of an equation of state, you just delegate the role of actually doing the calculation to the common workflow interface implementation. So now the question you might all have, I guess, is, does it work? Is it possible to really make it work for 11 different codes? And well, the answer I would say is yes. The thing I want to stress is that in the first paper, the goal was not about demonstrating numerical accuracy, but more to demonstrate the concept works and it's possible. We are now, we mentioned in a couple of slides, in the process of making a more severe or stringent set of validations, as Stefan mentioned yesterday, using this oxide set that Stefan spoke about. So these are, what we did was just to pick one example per category. We took an insulator, silicon, a metal, aluminum. We took a more complex material with a non-cubic cell to look how, relaxation works also when the cell is not cubic, like germanium telluride. And we also looked into magnetic systems. So we looked into ferromagnetic and antiferromagnetic BCC, BCC iron. And these are the results you get for all the different codes. And as you see, they're maybe not perfect, but already are in very good agreement, I would say. And the important thing is that there is always a margin for improvement in this automatic choice of parameters. As I said before, at the beginning, these plots were not as you see, or much worse. And we learned together what codes had to improve their choice of parameter, the choice of basis set, etc., in order to achieve this kind of level of agreement. And similar, just another example, we implemented a common workflow for the association curve of H2, and we ran it for all the codes, and this is the kind of level of results you get when you run these common workflows. Now, this already achieves a number of aspects. It's accessible, it's easy to be run, it's interoperable across codes, it's also actually reproducible. But in order to really make it accessible, we need to go even one step beyond, because a non-expert user might not want to install AiiDA and use the command line. So the first thing we do is we release everything inside what we call the Quantum Mobile. The Quantum Mobile is a virtual machine which contains AiiDA. It contains all the quantum codes I mentioned, which have an open license. Some of them just by license cannot be included. It contains all the AiiDA plugins and workflows. Plus, since May, it also contains the implementation of the common workflows, and actually more. It contains also visualization, etc. Actually, as a small disclaimer, if you're running a tutorial or a course where you need to have a virtual machine for your code, feel free to look into the Quantum Mobile or contact us. It's built in a very modular way, so it's extremely easy to, let's say you want a slimmer version, you can remove some of these codes, or you want to add something, it's very easy to do it in a modular way, so your code will stay there also in future versions. But focusing more on the common workflows, when you start, just download it and start this virtual machine, you get a Ubuntu terminal. You can just run the command I was showing earlier from the command line. I'm running here a Quantum Espresso silicon equation of state with a fast protocol. I just delegate it to the daemon. This means AiiDA will run it for me, will run or queue the various jobs. And this can run on your laptop, or you can also easily run on a different computer. At the end, you just run a command and it will show you the results. That's what you have to do. And since it was run with AiiDA, you automatically have all the provenance. This is to run those, but also from the tests we run in the paper, what we did is to publish on our Materials Cloud archive all the AiiDA export file and the scripts to reproduce it. So if you go to this specific DOI, you can actually look at it. You can download everything, the AiiDA export file and all the script to use it. And if you import it, what I did yesterday, I imported it in a Quantum Mobile and I connected it to Materials Cloud. What you can see, you can actually go and look at all the exact inputs that each of the implementers of the workflows decide to do. So here I just picked 3, for instance, for Custard, Siesta, and Quantum Espresso. If you know one of these codes, we recognize the inputs, hopefully. And just to give a sense, this was the input for germanium telluride, where we wanted to keep, during the equation of state, the volume fixed, but let the shape of the cell change. And here we can, if you know the code, you can go back and see how each code define this in a different way. In Custard, it write fixed vol true. In Siesta, it write MD constant volume true. In Quantum Espresso, cell do free shape. Very different way of doing it, but thanks to the common workflow, you just say it in a single way, and it's up to the common workflow implementation to write this in the right format. Now, I'm getting closer to the end of my talk. I wanted to briefly mention the current plans. Now we are already actively working in a second phase of this collaboration on the common workflows. We're trying to achieve a number of different goals. The first one, we are adding a number of new codes. 3 already are being added, and if you are interested, you can contact me. The Yuli KKR code, the GPO code in Denmark, and the Bin2K code. We are extending and increasing the number of common workflow interfaces that you want to implement for different codes. I stress that each of these common workflow interfaces requires sitting down and agreeing on what is the format of the input for a band structure, what is the format of the output of a band structure, a density of states, etc. So it's also not only, of course, the implementation of each of them, but also the first part is really a design of how the input and the output for each of these common workflow interfaces should look like. And we're already looking into band structure, density of states, and potentially projected density of states. And then also Born effective charges and dielectric constants as the ingredients to the actual common workflows for phonons, for instance, based on PhonoPy. The other important thing that was already mentioned a couple of times yesterday and by me earlier is that we are now wanted to use this to do a proper cross-active road validation, that's called a cross-verification of these codes in a more stringent way. And what we will do is to use this set of oxides that Stefan has been presenting yesterday. So 6 oxides per chemical element for the whole periodic table. where we'll run the equation of state for all the codes, for all the oxides, compare them and get comparison and try to improve, understand if there is margin for improvement. Many of the codes are also code developers involved. There are even people willing to improve the pseudopotentials or other aspects. So we are very, say, optimistic that this collaboration will really help not only validating the accuracy of the codes, but also implementing automatic recipes for anybody to run the codes at that level of accuracy. And the final thing I want just to mention as the final video before concluding is that all this has been designed with the idea that it can be used in a graphical user interface. All the inputs and which inputs are available to each code is machine inspectable. So it's very easy to convert into a GUI. And what we want to do is to implement a GUI for the common workflows into our AiiDA lab graphical user interface, which is a user interface for AiiDA based on Jupyter. What I'm going to show you is the current implementation for Quantum Espresso, but as you will see, it's already ready to be expanded to any code. The way it works now is essentially you have first a selection of a structure. You can do it in different ways, import from file, but also you can use, for instance, now the Optimade language to query any databases. And let's say you want to search for structure which contain silver, chloride, and oxygen. You can just click on a button, search for thanks to the Optimade API, look at the structure you're interested in, and press a button to then select the parameters. You have very simple inputs, which are mirroring the inputs I was mentioning earlier. But if you're an expert, you have an expert mode, then you can go in and change more advanced properties. Then you can just submit, and you let AiiDA and the common workflows do their job. You will have a way to inspect graphically what's going on, which steps are running, and if your calculation is running, you can look live to the output scrolling if you're interested. But what's important at the end, we just go and see the final result in a graphical form that you can inspect independent of the code. With this, I'd like to conclude. I just want to thank all the people who have made this possible. First of all, the AiiDA Materials Cloud teams, all the people contributing to AiiDA and the various plugins, all the authors of the Common Workflows project, but also all the new collaborators which are now working together for the next say, generation of Common Workflows. I'd like to thank also the funding which made this possible, in particular the NCCR Marvel in Switzerland, the Max European Center of Excellence, the Swiss Universities Fund, but also a number of European projects like Marketplace, DOM, Intersect, BigMap, and FFA, and a number of new ones. And finally, I want to conclude saying that on one side, I showed at the beginning how AiiDA and Materials Cloud make it possible to have fair access to simulation data. But at the same time, we also really were pushing toward fair simulations thanks to AiiDA and the common workflows. What we already implemented and delivered are open source robust turnkey workflows for materials properties. We have a common interface across 11 quantum engines, and more will be coming, which are very easy to use, but at the same time flexible for experts and designed to be interfaced to graphical user interfaces. And they will be the basis for verification and validation studies for this oxide set and the starting point for more common workflows. And with this, I thank you for your attention. I'm happy to take any questions.
Thank you, Giovanni. So for the next talk, I have a quick question. Sure. So you develop the common workflows across many quantum code. So do you think it's possible to connect this with the high throughput computing? I mean, by varying, for example, across different crystal structure or various doping element, etc. Combine these two.
Yeah, so that's exactly our goal. So what we actually did before, actually we are already using some of these common workflows for high throughput simulations. In particular, ourselves are mostly using Quantum Espresso. That's because our code of choice. And that's why the Quantum Espresso plugin and workflows are relatively advanced and contain a lot of robustness, as I mentioned. We are running, actually in 2 weeks, we'll be running on the next pre-exascale machine, Lumi in Finland, for a month. We try to fill this machine with, running hundreds of thousands of materials. Of course, what we want to do now, the other colleagues were doing the same with Siesta, with Castap, etc. And what we wanted to do is also to make it easy for others to run this. But indeed, the original reason we started all this effort was exactly high throughput simulations of materials.
Okay, thanks. Any other questions from the on-site?
There's one in Louvain here.
Thank you very much. It was very, very clear overview. I have one maybe a little bit provocative question.
Sure.
How far did you go in terms of testing to the real ultimate limit, right? So one of my former colleagues used to say, everything works for silicon, and that's the first paradigm of computational material science. And obviously you have the example of how well things work for silicon. What is the biggest, most complex systems that you can push through the common workflows without breaking everything?
That's an excellent question. And as you say, indeed, and this is what I mentioned at the beginning, the first paper was already just to convince first ourselves and then the others that it's possible to implement for 11 workflows, for 11 codes, common interfaces, which is already something which I think, to me at least, wasn't fully obvious at the beginning. Now, as I mentioned, exactly because of the question you're asking, what we are going to do is exactly this validation on the oxides, which I mentioned somewhere here. Now I lost. So what we will do is, let me see if I find it. There we go. We will test already any chemical element on all these oxide configurations for all of them. And this already, I think, is very powerful because it will also give us quantitative agreement or disagreement between the codes. That's not enough. Of course, there are more complex systems which will not work. And the point here, again, is not the guarantee. I won't guarantee that you take any structure, you put in any of the code, and it will always work. That's a part of the robustness I was mentioning, because many of these implementation I never saw. I mean, I had no idea of how the CS or custom implementation work. I trust the people using it. But these people are using these codes for their own high throughput research. And I can tell you for the quantum espresso part, for instance, that we are running hundreds of thousands of materials through this. We're running the whole ICSD, the Pauling file, the crystallographic open database. And thanks to a number of efforts, and again, I'm now going to speak specifically of quantum espresso, on the robustness of the choice of parameters, the robustness of the workflows and these handlers to know how to fix, but also the robustness of the underlying code, which is very important. We are now able to move from, I would say basically 50-60% with just running the code to 70-80% of success rate when running through the workflows to 99% success rate now by using a new implementation which is being developed at the Swiss Supercomputer Center, CSCS, which is called Sirius, which uses a variational method to converge the electronic structure and not an iterative method. So in order to really get to the final result of robustness, 99% robustness, you need to work a lot. It's not just about the interface. What I showed you here is a way to make it easy for people to run. And I think this helps a lot also for robustness, because once I give this to an experimentalist, I'm pretty sure after running 5 or 10 times, it will break it. But this means it's very easy to go to the experienced code developer and say, this material breaks, how do we fix it? So I think by making it easy, we also help speed up the process of robustification, if you want.
Yeah, thank you.
Any more questions? Actually, we enter into the last.
We have questions in Louvain. We have questions in Louvain.
Yeah, please.
So we know by now that the agreement between different DFT codes is quite all right, and yet in your approach you propose a 2-layer system into dealing with workflows. Do you think it would be feasible to have sort of a translator to have a unique workflow that would just direct based on the engine, will create the input file with the correct input variables, instead of redesigning every time you want to do a calculation with a different code, the workflow and the specific expert variables that one might want to use?
So I think it's an interesting question. I think the answer is it depends. So as you see here, the codes we've been dealing with are very, very different algorithms and basis sets. We have quantum chemistry codes like Gaussian and Orca. We have plane wave basis sets, Abinit, VASP, Quantum Espresso, etc. We have localized basis set, wavelets, and all electron codes, etc. So defining in a unique way what the right parameters are, I don't think it's possible. And maybe one important thing to stress is, of course, I could pick the, if I didn't care about the computational time, I had an unlimited budget, I would just pick a very extreme parameter for all of these codes. I would be sure they are converged and would be happy. Since this comes from a context of high throughput simulations, we want to find the smallest, but the cheapest parameters will give me converged results. So this will always be code specific, I think, especially if the methods are different. At the same time, once the methods are the same, like make an example, plane wave codes with pseudopotential basis sets. If you take a BNet, VASP, CASTEP, and Quantum Espresso, there we are working within the context of this collaboration to try to agree together, okay, the cutoff, which is converged is this mirroring we need to use is this, etc. But we did this design of having just a string and let the implementer of the workflow decide, exactly because the codes are so different, even if they compute very similar properties, which I honestly doubt that will be possible to do what you say at the level of the low-level calculations. But the good thing is that there are a few very important low-level calculations, relaxation, some basic properties, etc. All the rest can hopefully be built on top of them. And so when you define what an equation of state is, as long as the calculation is converged, you don't need to worry anymore, and then you just have a single equation of state workflow. I don't know if this answers your question.
Okay, thank you, Giovanni, for the nice talk. I have a very simple question. So I want to know if the AiiDA workflow can support the calculations considering spin orbital coupling, as well as if it is possible to produce the linear functions directly if I want to consider the spin orbital coupling. That's it.
Yes, so thanks. It's a very important question. So in general, again, maybe let me, just to clarify, maybe it's obvious, let me divide the common workflow interface from the actual implementation. So all codes that support spin orbit, you can run through AiiDA with spin orbit. In the common workflow interface in the first round, which is this one, we didn't implement or specify spin orbit just because we had to make some decision on where to stop. But already, like last week, we are discussing, and there will be a few more options to activate also, spinors and the spin orbit. So this will be possible in a few months. And it should be very easy to implement because for most codes, it's just a matter of activating certain input flags. So that's for the first part. So if you want the version you find online now, no, for the common workflow, but it will be there, I think, in a couple of months. For what concerns the vanilla functions, that's also another completely different topic if you want, but very important. And I'm working on this personally. Already last year, we published a paper where we show using the SCDM method, how it's possible to give a structure. And in the case of Quantum Espresso, run the Quantum Espresso calculation, then run the vanilla functions without having to specify the input, the input projections. There are a number of other efforts also in the literature in the past few years which do something similar, but what we did was fully implement into AiiDA, and actually there is also a tutorial online. Maybe when I stop sharing, I will put in the chat a link to the tutorial. So there is an example where you can, in a virtual machine like Quantum Mobile, you put a structure and we give you the final vanilla functions and interpolated band structure for you. And what we are doing now is not part of what I presented, it's part of our research. We have a new improved method for automatically choosing the vanilla functions and finding the vanilla functions, which is much more robust also in the case of spin orbit, which was a bit, I think, the weaker aspect of the SCDM method. So hopefully this is something we're going to run in this big run in Lumi in a month. And so hopefully by the end of the year, we'll probably have a preprint where we explain this and also the code will be available.
Thank you very much. Looking forward to your progress.
Thanks.
Yes, another question a bit related to what was already mentioned, but I have seen that you plan to have the phonon calculations implemented on top of PhonoPy, which I can understand because I guess this will be a very general tool for all engines to be able to generate the phonons. But on the other hand, one also knows that using DFPT is more well efficient in order to compute phonon band structure. What is your plan in the future with respect to such formalism like DFPT that are not implemented in many codes, but still can be very useful in some situation?
Oh, that's an excellent question, thanks. And indeed, I mean, I realized when I'm now coordinating this project with 20, 30, 40 people, maybe more, it's very important to try to be kind of concrete and practical and decide a minimal deliverable which is still valuable. and then build on top of it with the idea that this can be extended. So in practice, we decided to go for PhonoPy just because in this way, we demonstrate the value of this common relaxation workflows, and because it's easy to do for all codes, as you say. But once the common interface to run a phonon calculation through PhonoPy will be written down, and this will happen hopefully in the next 1 or 2 months, it's going to be, say, easy, quotation mark, it's clear, let's put it this way, I mean, not easy, but clear for an expert person of a code, could be a BNet, Quantum Espresso, or any other code implementing the FPT, how to just map the common inputs to their own workflow inputs for their code to run the FPT. So I don't see, so the fact that I mentioned PhonoPy is just a practical issue, just to demonstrate it works and make it available for free for all implementations. But definitely I see, codes like a BNet or Quantum Espresso implement, or many of them already have actually Python implementation, I guess AbiPy for you and our AiiDA workflows for us, which can compute phonons for the FPT. They should be at the point relatively easy to map the common inputs to those workflows.
Thanks.
Okay.
In a sense, just to conclude, in a sense, this will give the responsibility to the user to decide at point which implementation to use, and they can also actually compare and things like this. Sorry.
Okay, I have one more question. So I think the point to have these common workflows to compare performance among different codes. And then for example, I show some, even the overall agreement is good between different code for aluminum equational state, for example. There are still some small difference. So in this case, we want to make sure we do apple to apple comparison. I think the biggest, well, of course, we can choose the same functional, no problem. But I think the biggest possible difference among the code are basis set. So I think it's very hard to compare like a plane wave and the numerical basis set and the local basis set like a Gaussian type or Slater type. For example, the 400 EV in plane wave cutoff is equivalent to, it's a triple zeta in numerical basis set, or 6311 G++ in Gaussian basis set, etc. How could we make a real, I mean, they are equivalent in terms of basis set. I mean, the level of convergency, as you mentioned earlier, 90%, we cannot reach the full convergency for sure. For practical application, we want to make sure we reach the same level of convergency. So in both, in all cases, there's, for example, 90% of convergency. That's a fair comparison. Otherwise, if there are any difference, we are not sure where it's from. It can be just convergence level are different.
Yeah, no,
and
that's
the same thing for the shoulder potential, right? They could be different. Yeah, that's sort of.
Yeah, so maybe to answer that, indeed, the first thing you want to compare the same level of theory. And in this first demonstrator, if you want, we used only PBE, but we're already discussing how to make for the DFT implementation. And now they are all DFT, but in principle, the common interface could work also for non-DFT. But for the DFT implementation, we are now defined how to define in a common way the functional based on DBXC. That's what our plan. So we will be able to switch this. Now, in terms of basis set, you're right. That's the main difference. But as you see here already, of course, there are differences. Like CSAO for some reason is different. This might be because of the basis set. But indeed, the way I agree with what you say, the way in which we can decide if two set of parameters for very different basis sets are equivalent is exactly by having a quantitative error. And this goes also in the direction of error estimation of DFT calculations, because no, you have here all electron, plane wave, localized basis set. We can say if the delta factor is within 1%, that's the kind of level of accuracy we want to achieve. And that's what for us means having a precise protocol. Maybe a fast protocol means 10% and a moderate protocol means 5%. So indeed, the way I see we can make this equivalence is by looking at the results and defining an accuracy level and making sure all the results are with that accuracy across the periodic table. An important point you mentioned correctly is for pseudopotential code, the pseudopotential. That's why I say the good thing that for the elemental element was already shown in the delta study. We have now pseudopotentials which work relatively well. what we will see now, that work Stefan is doing, and was already shown yesterday, and we will hopefully do more in this in the context of this work. Sometimes the pseudo-potential may not be good enough yet for more complex system with oxides and different oxidation states. So indeed, this work might point out the need of improving certain pseudo-potentials for certain codes. But one thing we try to do is to compare also very similar codes, let's say, I don't know, Abinit and Quantum Espresso, trying to use the same pseudo-potentials, same cutoffs, etc., to see where the discrepancies come from. And actually, I can tell you one thing which maybe was a bit surprising for us, is that there were kind of important disagreements due to this choices mirroring and sizes mirroring for metals. So even things which one might not think immediately to are at this point start to become the important discrepancy reasons. Here, I just maybe show an example of a preliminary result of Quantum Espresso runs against Bin2K runs by Stefan. And some come very well, some come very different. We are in the process of investigating why they're different. Some can be pseudo-potential, some can be smearing, some can be something else. Our goal is by the end of the year to get to a very good agreement for all of them, for all the codes.
Okay, thank you. So we still have 15 minutes for the discussion. I think this is the discussion session for all talks. So if anyone have questions about NOMAD, so I think, yeah, Markus there is waiting for questions, right? I have some questions about NOMAD. I think the first question about NOMAD is about impact, how to evaluate the impact of NOMAD. So my personal thought is we cannot evaluate a NOMAD as a, of course, if the publication is one of them, but it's not a major merit for evaluating NOMAD. I think, so now people are proud of a number of papers indexed by ICI, for example. But in future, would it be possible people are part of how many my own data are indexed by NOMAD, by giving NOMAD DOI. So number of data indexed by the NOMAD, maybe if we become a kind of standard in the field, I think that's a value of NOMAD or impact of NOMAD, just like ICI or other similar merit. Another thing is that I think the number of users or number of access users or the number of local copies download. That also, I think, it's an important measure for the impact of NOMAD. I think that sort of thing, I think more practical rather than just number of publications or because this is a database should be used in practical application. That's kind of my view. I think also similarly for the AiiDA workflow. So if that workflow, I think is very common to many code, if it can be shared or standardized, so people don't have to develop their own workflow. And then that's also easy for comparison for different system, something like that. So standardization, I think it's at the biggest impact of NOMAD. Also, I think AiiDA workflow.
I think
that's my personal thought.
Yeah, let's take this as a very general question to all kind of databases, code systems, whatever, right? Because this is basically, you can ask this to everything, how to measure the impact of some methodology, database or system. And I think that's the problem with metrics overall. And there's also a big discussion in publications, I think, is that if you just count numbers, you often miss stuff, right? If you think about calculations, for example, they could be very, very compute intense and work heavy calculations that people have put in much work and stuff like this, and others are just run like the full thingies that you just try out when you download the code or something like this. Right? so it's really hard to make a comparison just by numbers. But with metadata available, maybe you can make a better assessment and say, okay, this is like a calculation, or this is like a property computed with has a like giant workflow behind it, and it was run like for weeks on an HPC system, and this is something that just someone computed on his laptop in his time. These kind of differences you want to capture. And I think the user numbers, that might also like be super deceiving, depending on how you lure your users in, and how you, I don't know, capturing what does it mean to use a system well, and use the system with some impact. Only the numbers is like also very difficult. And the other question is, of course, what do we actually want to have with these impact metrics? What do we want to measure by these impact metrics? Of course, it's important feedback for the database, for example, to see where can we improve, and how does it develop? Like, do we get more impact or less impact, and what can we improve on the platform? That would be one thing. But besides this, why is it so important to have these metrics, and what are other use cases for these kind of metrics?
Okay, thank you. Also, another comment is about the fusion of data. So, I think now we mainly focus on vast data calculation as the AiiDA's or effort. So there are so many quantum code. So if we can fuse the data or combine the different quantum code, result, and put into one big database, because they share the common, say, properties like elastic constant, something, and then that would be make the NOMAD even more useful, and become sort of more unique. If someone want to do AI analysis, you have a better or bigger combined or fused database, and then people prefer to use this one, or probably the only choice. Then that would be make NOMAD like a unique choice. And then that, well, of course, cite NOMAD, because there are no other place can do this. They cannot hide this fact. And then that would be, I think, another way to, to become more unique. That's another way to make a more impact. That's my point.
Yeah. That's maybe also not really a NOMAD question, because we have to be honest here, right? We to some degree, we are competitors. We have like different people, different databases for different needs, and with different use cases in mind. But in the end, we are also like kind of competitors, and trying to find impact in the same sphere of influence, so to speak. But I think it's fair to say that most of the databases out there, systems out there, that they have their specific applications and specific niche. No, not niche, that's the wrong word. I don't want to bias this. Like if you look at it, it's like trying to be very general, trying to offer all kinds of data from everybody, and then trying to have the metadata. But this also puts a lot of burden on our users, because they have to identify what are the good calculations, what are the bad calculations for them. And other databases, for example, or something like the cloud might be then better for them, because it's more specific. It's easier to find like high value kind of workloads run in certain systems that you're interested in, then it would be on NOMAD. So I think that all the competitors out there, so to speak, have their own kind of thing, speciality. But anyhow, in the long run, it would make sense if we like, and Optimate, for example, is one of these initiatives, like where we try to put effort together and try to standardize something that connect the different systems a little bit at least. So yeah.
I was actually going to comment on that line. You're perfectly right that we cannot avoid some form of competition between different projects. And so, I think that the way to go is indeed to have the same query language to query the different databases. And then from the user point of view, it doesn't care whether the data is here, there, or elsewhere, provided that he can query the database in the same way.
If I can add maybe two comments, one on a previous question about ontologies, and then another comment. So the first one about ontologies, indeed, the way we see our common workflow implementation is a kind of a way to help defining ontologies for material science. So by having now an implementation that works with some kind of standardized input format, is not yet at the ontology level, but it would make it easy now to, and actually next week there is a workshop about this where actually many people and probably here are all going also to participate exactly on ontologies. And I think my idea is that we can use these or other similar efforts like ASR from the ASC group to define ontologies for material science. And this part on ASR actually comes to the question of Markus that he wrote in the chat, so maybe I try to quickly reply to that as well. He was asking how our effort compares to other workflow engines, in particular like exactly ASC and ASR. So I think ASR is in a sense in scope is very similar. They also define the concept of what a calculation is, and I have to say they are much more advanced in the list of properties they can compute. They have a quite very extensive long list of properties. On the other hand, I think we are more advanced in two aspects. And again, it's not a competition, just to, I think, to say what the status is. On one side, I think is the robustness aspect, where in AiiDA we have all these features in many of the codes to take care of failures, and they have this concept of restarting, etc. It's not just a single run. And the other thing is that they acknowledge in their paper, in the ASR paper, and the conclusion that while the concept is exactly designed to be decoupled from the actual code, they acknowledge, I'm reading here from the paper, the coupling is not in place, and the majority of recipes are actually specific to the GPO electronic code. So I think that's okay. Of course, it's a starting point, and I'm pretty sure being based on ASC would be easy for them to extend to more codes. But I think we went into kind of two orthogonal but both very important directions. For them, it was to define as many properties as possible. For us, was to define few properties to begin with, but implement them from many codes. And I think putting these two together will be very powerful. And if I see also potential for interaction between the implementation at some point, which doesn't mean reusing the same implementation, be one calling the other or things like this.
I think this is a good general point, right? Because when you want to overcome heterogeneity and join information in general, going for the overlap is always like pretty easy, but usually overlap's like super small. And when you want to go away from the overlap and go into the specifics, which often is necessary for many use cases, then it becomes like far more complicated. And these are the challenges that I think most of the databases and everyone is facing. It doesn't really matter if you want to integrate a calculation to a workflow system or into a database or make it available through API. There's then always the same questions. How can you standardize these specifics? And with Optimate, for example, we are at a point where we're very good at defining the system and everything goes in there. But then when we think about workflows, when we think about properties, then it becomes far more complicated because everything then so different.
I was going to add in the same direction as Giovanni was pointing. So the effort of the common workflow is there's one workflow for different codes. And now we have the other step that we have to bridge, I would think so, is that there are many different workflow managers, and it would be nice to have some kind of common workflow language that is accepted by the different workflow managers in such a way that then, you can have the different workflows managed by different workflow managers with different codes, ideally. That would be indeed very powerful, but it's a long way to go, I think.
If I can give a direct answer to this, to Gianmarco, I think one has to be, I think my gut feeling, I don't have a response, but my gut feeling, one has to be careful at which level one want to make this common. Of course, many of all of these workflow engines, AiiDA, but could be ASC, could be Fireworks, have their own specificity and the reason they are like this, and actually it's good, sometimes they're a bit different. I think it's a bit dangerous or risky to try to really go to a kind of converter of the workflow between one language and the other. I think a practical approach would actually be to maybe exactly on the direction of ontologies. So we agree that the concept of relaxation of a crystal, so what is a crystal structure? What is the concept of relaxing a crystal structure? And through an ontological definition, we have a way to say, I want to do this relaxation for this structure with workflow engine ABC. In a sense, it's going one step further. What we did for, I want to relax with this code, we would do for the workflow engines. And then I think this could be a practical way, because in practice, because of technical and maybe also psychological or historical reasons, it's going to be very, very tricky to merge them, which I think is not possible. But also converting between them, I think that even if they're all using Python, it might still be technically very challenging. You have to read the Python, parse the Python code and convert. So maybe that's not what you had in mind, but yeah.
No, I fully agree, Giovanni, that it's not something that's going to be easy. But I mean, if you take the point of view of a developer of a code, I mean, once you know, or a developer of a new functionality. Okay, so for instance, we've been working here on an electron phonon coupling, and so we've been implementing a workflow first in the Python package that controls AiiDA. But then, I mean, ideally, we'd like that workflow to be usable by the different workflow manager, and otherwise, it means that we have to implement that workflow once in ASR, once in Fireworks, once for AiiDA, and you know, if some other people come up with another workflow manager, then it means that from the AiiDA point of view, we need to develop plugin for every single thing. So that's not feasible.
Oh, I totally see, and I see your point. I think I get it. The challenging part will be to understand at which level the things are common, but I think you have your specific use case is very good because you're interacting with probably all of them. So you really need to, I know you're planning to solve this issue. So
hopefully.
So I think when we talk about what Markus just said, right? I think the first and maybe the most important step is to recognize the steps in a workflow that has been used, right? Not necessarily that you go from this is my abstract definition of a workflow to doing this workflow in different managers, but be able to kind of see that this workflow in this manager is the same in a certain sense to what you have been doing with another workflow, right? So that you kind of pull this metadata out of one workflow or another workflow from different parts, right? So that you can kind of merge and be sure that you have the same data. And then the design of a certain workflow can be kind of compared to the design of another one. If you kind of have these ontologies to kind of map an abstract workflow to the different ways it has been implemented in the different packages.
Perfect. Actually, now it's the time of ending this session, but of course we can continue a little bit. Any more questions, or just we finish? Oh, seems
we have one question in Louvain.
Yeah.
So thanks for the for all the people here. That I want to ask for the database developers and the framework developers that if you can share some experience with the like DFT code developers. That for example, if when you develop the workflow, like in AiiDA, you have something like every code can say that I want some calculation to be with just input of precision with high, then perhaps every code is working on to simplify the user input to achieve this, but they are all having their own recipes. So is it possible that like the framework developers to share the experience, or to make it possible to for the DFT codes to make a common effort to make a recipe on how to make this possible? And another thing might be that for the to define perhaps what the future DFT code should do to adapt to the frameworks. Like every DFT code has its own method to do the relaxation, to do the MD and things like that. But and now in every framework, I think that is also implemented. So perhaps for some DFT code, it doesn't have to put a lot of effort to do this, but it's possible that if you can share the experience or how to make the code more adapted to the frameworks, and also the input and output, how to make them more easier to be passed by the framework and the databases. And also if we have a standard like input output, when we put that into the database, now that if all the data is stored in some kind of database, but still sometimes we want not just the data from there, every code has its output, which has its specific output, which is perhaps not inside the database. And if we can make an effort to standardize the outputs and inputs, then and also the post-processing scripts to then that can be shared by all the codes. I would like to know your opinion about the impact when these data frameworks can make this happen.
Do you want to start, Giovanni?
Maybe I can just give a quick answer. Then unfortunately I need to run away in 2 minutes because I have a doctor appointment for my kid. So I'll go and I'll let you continue. So it's a very important question. I can tell you practically what we've been doing. So already in our specific high throughput runs with Quantum Espresso through AiiDA, we've been in contact all the time with the developers to give back the feedback on what we learn about the codes and code failures. In the end, many of these codes have been designed before the era of high throughput, and so they would run for simple inputs. But when they're put to the test of running a lot of materials, a number of things happen. So that's definitely something very important. I think for any other workflow engine, other workflow developer, having a direct contact with the developers of the code is key. Also because for me, the things, part of your question was about what can we do to make the codes easier to interact. I think there are 3 important things I see from my experience that code could do to be ready to be interfaced with a workflow engine, etc. It's not much for me having a common input or common output. That's something we can define a posteriori. We have been writing a lot of parsers. The NOMAD have been writing a lot of parsers for various codes. Of course, if we cannot unify, it's good. But for me, the important thing is reliable format for the output. So a machine can parse it independent of the version of the code. The format doesn't change, so the parser doesn't have to change. A reliable way to detect warnings, errors in a robust way, because you want at least to detect them and inform the user there was an error. And more generally, that's maybe the most important thing, is the robustness of the engine. You want, and many of these robustness aspects, capability to converge to a correct solution without crashing, is something that very often has to be or should be implemented in the code. And in this sense, interaction, I think, with developers would help. Of course, the workflow engine can do some tricks and workarounds to try to make it work, but very often, as I mentioned earlier in my example, we went to 80% to 99% success rate because the code changed the algorithm, not because we fixed something from the outside. And the final note, there's a different community, the MOL SSI I'm aware of, that actually they managed to kind of put together people and really have a kind of common format for inputs and outputs for quantum chemistry codes. That's quite interesting as an effort. I think it's a bit more challenging for us in practice. And again, I think it's not the first priority. I would say it's the second priority. That's my comment. And then maybe I'll let others, maybe Markus or others reply. Yeah. Unfortunately, I need to leave, but I will be there in the afternoon. Sorry.
Thank you, Giovanni. Yeah, I can put a few cents to this. So first of all, I agree with what Giovanni was saying. And yeah, when you look at this, it's like different levels. I would say first is like the data format itself. Like putting out ASCII files doesn't make it easy to parse them, right? If the data format itself would be like more formal, let's say you use HDF5 or you use JSON or you use XML or whatever, that would be the first thing that makes it much easier to consume the data that you're producing. Also for inputs, it's the same thing. And it's like, I think that even the code developers should think about this, finding definitions and schemas for the data. And you have all like written documentation and stuff like this about what the different parts of the output mean or what the user needs to be inputting. But if this schema could be formalized as part of your code base, basically, right? It should be part of your software that you say this input has this name and means that this and that and has this unit and shape and so on and so forth. These kind of schema information would be there, and then it would also make it a parser developer, for example, or someone who wants to integrate the data would have a much easier job. Or deriving ontologies for all this information would be much easier if there would be also already some kind of formality behind the data that you use it as inputs and outputs. So for a very long time, code developers basically just being on their own, developing their code and being fine with this, and then physicists trying to understand this. But then you have like all the workflow engines, like ASE, for example, is like trying to build all kinds of parsers and producing inputs for various codes. The AiiDA guys are doing this, NOMAD guys are trying to produce parsers and something like this. And Giovanni is fine with it, but I think it would still be much, much easier if like you would make it easier for the puzzle developers to build these kind of things. But in general, data integration and data formats, it's like a messy business. It's probably not 100% avoidable, but going for some levels of standardization would be great. Even if it's just bits and pieces, like for example, you could pick up on the Optimate standard to just have a common format for inputs, like how to define a system, for example. And just already make stuff much easier. You saw this in Giovanni's presentation. He was like integrating with other databases using the Optimate API, and you suddenly can pull a crystal from this and there, and then put it to your workflow. These kind of things would be then possible. Yeah, and of course the ontology thing is something that we should pursue as a community as a whole, right? And everybody should take pieces of this and try to integrate their parts of the chain with it, like being a co-developer, or database maintainers.
Yeah, I fully agree. So it was pointed actually by Mikil a bit earlier that for the input-output, I think that there would need to be something which is an API, again, that is kind of stable in time, and to which the different codes can then write their specific Python interface in such a way that, you know, they are responsible on how they generate the input from something that is common to all the code to something that is specific to their own code, and then they translate the output of their specific code into something that is common. I mean, that's some work that we did in the framework of ABIPI, where we translated that into stuff that was understandable by Pamagen, but it would be ideal if there was something that was understandable by many different things again. So that's this kind of API common to many different things that would be ideal to define in some way. And indeed, Optimate can serve as an umbrella for developing something like that.
I think it's very important but because if you look at the whole chain, yeah, there's so many translations involved, right? Yeah, so like, let's say you take a code, it takes input from something like ASR or what we just saw. So there's one translation for the input, and the code produces something. It has to be passed again by the workflow engine to make sense of it. Then the workflow is putting everything together, also producing some form of data. Then the database like NOMAD picks it up and tries to parse it again. And then in the end, you have so many translation steps that lots of stuff gets lost in translation. Right? Yeah. And if we could agree on a common ontology and then derive of this on a common format for like most of the information that we have in material science, then it would be much easier, because everybody could already put the information already in a form that's that everybody understands, and then there would, like, we would all speak the same language to keep up with the translation metaphor.
Indeed.
I guess it all starts with machine readable output, right? I mean,
yeah, that would be the big
one. Fast made this step to XML output. In Abinit, we have the netcdf files, and that basically means that it is something you can read and that can afterwards be, you can add things to this, right? And it's still there, but what you have there is still there. But like parsing these human readable output files that then from one version to another version have one empty line somewhere more, that's obviously the biggest horror nightmare for all of these frameworks. So I think, if anything, that would be the lesson, or like the message to the code developers, right? Please provide stable machine readable output files.
Yeah, that's totally right. That it has some baked in backwards compatibility. You could just, with XML, you could just ignore stuff that you don't recognize as a parser and still pick up on those things that you know.
Yeah, exactly. So that it stays what it is, right? So that the output stays what it is, and that there can be more. Like XML will do this in trees, a JSON file will do this. If it's just a dictionary, you just pick up what you know, and what you don't know, you leave, or you kind of add the procedure in there. And the same goes for the netcdf or HDF5, right? So it doesn't really matter. I think then in the end, it doesn't really matter that much, as long as we at least start to stick to this paradigm.
Maybe you can stop here in order to have a decent lunch.
Yeah. So maybe, yeah. So thanks all the audience on site and online also. I think as a few words, I would like to add a little bit more. So I think we have a big word, so we allow the freedom and you know, of course, we hope we have more standardized format and input output. Also, AI may handle some integration standardization, but actually that's the point of a big database. So if the result from different code come into the database, they have to be standardized or they show their original intrinsic meaning. So that's also a way to move to the unified knowledge or that by the database, or even across different format or for different database. I think in scientific world, still we have more unified or common language than political or other system. So that's my ending words. So thanks for everybody. I think I finished my job today. So thanks for the invitation. I think maybe also interesting across different part of the world, the conference. I think we have also do broadcasting online in China. We have a lot of Chinese audience, not in this room, but online. So, so thanks for this great opportunity to share the knowledge and your suggestions. So I think I finished my part. So thanks for your invitation. Thanks again. Hopefully see you sometimes again. So back to the host the conference in Belgium. Yeah.